the next topic will be about requirements engineering. No, requirements engineering is a critical phase, no, in software development, no, involving the process of gathering, no, analyzing, and validating requirements to ensure a successful project outcome. No, it aims to define clear, unambiguous, and achievable requirements that reflect stakeholders' needs, serving as the foundation for design and implementation. So requirements engineering helps, no, to avoid misunderstanding, mitigate risk, and increase the likelihood of developing a product that meets user expectation. Now, requirements elicitation. Requirements elicitation is the initial stage, no, of requirements engineering, where the goal is to identify and understand the needs, no, expectation, and constraint of all stakeholders. No? Especially again, if we are designing or creating a customized software. No? This process, no, involves collecting information through various methods, no, such as interviews, surveys, focus groups, and observations. No, effective elicitation, no, ensures that requirements accurately capture stakeholder goals. Wait, off ko na lang. Okay, paving the way for the project that aligns with business objectives. There are certain techniques actually for requirements elicitation. How? The several techniques can be used for a requirements elicitation, like interviews, because interviews allows for one-to-one discussions with stakeholders, providing insights for their expectation. It is very important for us who assigned to develop the software. No, another is the survey, because survey gathered input from a broader audience, while focus groups bring stakeholders together to discuss ideas collectively. Let's say, for example, if that is for finance department, so better for you to meet, of course, the finance head, the person who will be able to utilize the software once it is created. Then, of course, another thing is the manager, no, the owner of the company. No, so observations also involve studying how end user interacts with existing system to identify pain points and improvement areas. Each techniques, no, provides valuable perspectives, no, allowing engineers to create a comprehensive requirement list. The problem sometimes, of course, is our students. No, they were not able to conduct observations, no, or surveys. No, minsan it happens, no, especially in the undergraduate program, na talagang ang nagsasagot ng survey mga kaklase, hindi talaga yung target users. Na? That's why during final defense, we encourage, no, it's not encouraged, they are obliged to bring the department head of the department na gagamit na kanilang systems para malaman natin na yun talaga yung kanilang requirements. Okay? Each technique kasi provide valuable perspective, allowing the engineers or the software engineers to create a comprehensive requirement list. No? Kailangan meron tayong list. No? Let's say module 1, check. Module 2, check. Module 3, check. And so on. Now, how about the requirement analysis? No? Right after listing all the modules, we need to analyze, no, these requirements. Now, once requirements are gathered, the next step is requirements analysis, right? And this phase, no, involves examining the requirements to identify any ambiguities, no, inconsistencies, or conflict. So analysis helps refine the requirements, no, ensuring they are feasible, realistic, and aligned with project goals. Baka naman may hinihingi yung users na hindi naman siya aligned. Na that's additional feature na kung wala naman yun, hindi naman maapektuhan ang flow ng operation ng financial department. Something like that. And the analysis phase also allows team to prioritize requirements, no, focusing on those that provide the most value to stakeholders. Pwedeng, sige, pwede naman, we may consider your proposal, but it is less valuable. So what we're going to do is to look for the most value to the stakeholders. Then after that, how will be able or what will be the methods for us in a requirements analysis? No, various techniques can be used to analyze requirements. No, this include modeling, no, which visualize requirements through use case diagrams. Yeah? Alam ko lahat kayo marunong gumawa ng use case diagrams. And the most commonly, pero ngayon parang bihira nang gumagamit, the data flow diagrams. And the most important for database, no, is the entity relationship diagrams. So most commonly, during chapter 1 to 3, we as professor only asking about the prototype. Now, prototyping is another approach that allows stakeholders to interact with early version of the system, offering feedback for refinement. Requirement prioritization methods such as MOSCO, must have, should have, could have, and won't have. Dapat ganun eh. Di ba? Yung Moscow, di ba ganun? Must have, ano ba yung mayroon dapat? Should have, ano yung could have, and won't have. It helps the teams decide which features to implement first. That is through the methods of requirements analysis. Then afterwards, we need to have a requirements validation. Now, requirements validation ensures that the documented requirements accurately reflect stakeholder needs and are technically feasible. Minsan may mga panel na parang out of this world. That's why it is important for us to define as early as possible with sa galing sa stakeholder. Ito lang talaga yung need nila. Kasi si panel, how about if you wanted to put a blockchain technology? Hindi naman capable yung company, yung target clients natin. But if your proposal, let's say for example during your thesis, no, in this MSIT, is an open software, no, I mean what I mean to say is generic. Wala kang target na clients. Ayun, doon pwedeng magdagdag si panel. Kasi wala kang requirements analysis at requirements na hinihingi yung client. Kasi nga generic. So pag sinabing generic, see to it that you could able to, let's say kung mayroon na sa market, lahat ng modules na mayroon doon makukuha mo, then magdadagdag ka pa na additional modules. Ganon kapag generic ang ginagawa mong software. Now, again, requirements validation ensures that the documented requirements accurately reflect stakeholder needs and are technically feasible. So kapag yan po ay kung kayo po ay gumagawa ng customized software, kung ano lang yung list na binigay at pinirmahan nung may-ari ng company, hindi pwedeng lumabas si panel doon. Dapat within this But during the pre-oral defense, better kung nandun yung pinaka-manager na stakeholders para pag may suggestion si panel at na-realize ni manager na pwede, saka lang siya ma-accept. Pero kung wala doon, hindi siya pwedeng basta magdagdag. So, ilalagay mo lang yung sa notes, then i-discuss mo sa stakeholder manager, then kung mag-okay sa kanya, saka lang siya ma-add sa list as your additional modules. No, because requirements validation involves reviewing requirements with stakeholders and conducting tests to verify their accuracy and completeness. So validation activities such as walkthroughs, reviews, and testing help identify and resolve any discrepancies, ensuring that requirements align with project goals before moving to design and development. Parang di ba, kung ang bahay ginagawa, naggaano mo na ng plano, same din dapat sa software development. Kaya uso yung prototyping. Ano po? Kailangan may prototype tayo. Pwede nga gamitin natin is sa database, syempre entity relationship diagram, pwede tayong use case diagram doon sa design, and sa development, pwede rin naman tayong gumamit ng data flow diagram and other graphs. No, pwede naman po yon. So, what will be the importance of clear and unambiguous requirements? No? Kasi kung napansin ninyo ba na talagang by detail, no? Clear and unambiguous requirements are essential for a successful project. Take note, for how many years? It's just only 10 to 20% successful major projects successful lang po ha. Ganun lang kaliit ang naging successful project. No? So, ambiguity can lead to misunderstanding, no? Resulting in software that doesn't meet stakeholders' expectation or requires costly rework, no? At hindi naman advisable 'yon. Pag-uulitin, additional week, additional pay, with electricity, with payroll and everything, no? So well-defined requirements ensure that all team members have a shared understanding of project goals, reducing the likelihood of misinterpretation and enabling more effective communication throughout development. What will be the risk, no, of ambiguous requirements? Ambiguous requirements can lead to scope creep, as what we discussed earlier, misalign expectations, and increase costs. When requirements lack clarity, developers may interpret them differently, leading to inconsistent implementation. And this can result in additional testing. Ang mahal ng testing ha, kahit pasabihin natin yan na basic ano pa lang tayo, no? Rework, no? Or even project failure, no? Avoiding ambiguity is critical, no? To ensuring the development stays on track and produce a product that meets stakeholder expectations. Now, what will be the techniques for clarifying requirements? Kasi dami namin sinasabi ng aming professor. So paano ba? Ano bang techniques ang pwedeng gamitin para dun sa pag-clarify ng mga requirements ng aming target clients or stakeholders? To ensure clarity, no? You as a software engineers, no, can use techniques such as requirement specifications, dapat meron kanyan, which provide precise description and outline all key details. Now, so kung itong module na to, anong mga laman, ano yung mga sub-module, dapat nakadefine yon. Ano po? Modeling and visual aids like flowchart and wireframes, because it offers visual representation that help stakeholder understand requirements more clearly. Kasi hindi naman po lahat ng ating clients ay IT person or IT related yung ano nila, or they are not technically equipped when it comes to our software development. So if we could able to provide, no, a modeling and visual aids katulad po ng mga flowchart and wireframes, these stakeholders understand requirements more clearly. So creating prototypes, again, or mock-ups, allow stakeholders to interact with early representation of the system, providing feedback to improve clarity and reduce misunderstanding. Now, syempre, right after ma-present, there are certain cases that there are certain changing requirements, no? So, and kung ito yung naalat natin ng first day, ito yung price, di po ba? So, how about if there parang, okay, hindi ko na kailangan itong module na to, or I need additional module for this. In many projects kasi, no, requirements are likely to change due to evolving business needs, technological advancements, or stakeholder feedback. Eh, naku, hindi namin kaya ang cloud. Naku, hindi namin kaya ang third party ng ganito. So, effective management of these changing requirements is essential to maintaining project stability and preventing scope creep. No? So, managing changing requirements involves implementing processes and tools that facilitate tracking, evaluating, and incorporating changes without disrupting the project process. So, what will be the techniques for managing changing requirements? Siyempre, di ba? Techniques for managing changing requirements, no, include version control. Kaya makikita, di ba sa ISO nga po, meron tayong mga papers na nakalagay doon is version 2, version 3, and so on, where different iteration of requirements are tracked and documented. Still, documentation is very important. That's why sa team ng software developer, may isang documenter dapat. So requirements, traceability matrices, yung RTM, no, help team trace its requirements back to its source, ensuring that any changes, no, align with project objectives. So agile methodologies which use iterative development cycles allow for flexibility in accommodating changing requirements while maintaining project momentum. So what will be the importance of communication in requirements management? Napakahalaga, no? Effective communication is critical in requirements management, as all stakeholders must be informed of any changes and their potential impact. Dapat alam nila, kapag nagdagdag ng module, tatagal. Kapag nagbawas ng module, hindi na pwedeng bawasan yung price, and so on and so forth. No? So regular meetings, clear documentation, and change control processes ensure that all team members stay aligned. So when communication is effective, it reduces misunderstanding and ensure that everyone remains informed about updates to the project. No? So, ano po bang benefits ng requirements engineering? What will be the benefits of requirements engineering? Take note, class. Requirements engineering provides multiple benefits, no, including increased alignment with the stakeholder needs. It reduces development time and improve quality. Because I believe by carefully defining, analyzing, and validating requirements, the team can minimize costly rework, no, enhance customer satisfaction, and deliver a product that meets or exceed expectation. Effective requirements engineering also enhances collaboration and accountability among team members. Okay, so I just want to play a video presentations again. Looking forward, that's just only around. Ayan. As additional input. Actually, software engineering is very interesting, especially for those.
Go ahead, whenever you're ready.
All right. Good morning, afternoon, evening, everyone, whatever time you end up watching this video. Welcome to the course on requirements engineering. My name is Birgit Penzenstadler, and today I will give you a little overview of what the content of the semester's course is going to be. So let me start with writing down that title, Requirements Engineering. You probably have that somewhere on the website that you're looking at. However, one of the most important things in requirements engineering is becoming clear about the terminology that you use in a certain context. So the first thing I would like to explain is what requirements engineering is. It has two parts, requirements and engineering. It's the early part of software engineering, software design. So in software engineering in general, we start eliciting the requirements from the stakeholder. We then move on into software design, and then we implement and code, and then we test, integrate, and eventually deploy. And then we'll have to maintain for a long time potentially. And you can see by the gesture that that usually takes more effort than you would initially think. One of the reasons why it often takes more effort than you would initially think is because people didn't do a proper job in requirements engineering, which will never happen to you because you're learning it right now. So requirements are what people want in a software system or in a software-intensive system, or actually in any kind of system. So what you learn in this course is potentially going to be useful for all sorts of areas in your life. Second, it includes wishes that they may have that they are not aware of yet. Third, it includes what they actually need, but they may not know what they actually need. They're stuck with some of the wishes and some of the things they think the software system should be able to do. And the last one is constraints. So constraints that your technical environment brings, constraints that any other software system brings that your system will have to be integrated with, and constraints by the operating environment where your system is later on going to run. For example, a certain connectivity to the cloud. That's for the requirements part. For the engineering part, engineering in general says we try to do things according to a certain systematic. We try to follow some good practices. We will have some guidelines. We will have some frameworks. We will have some rules. And we will have some best practices that have developed over experience in many years. So even though we cannot formally prove why that is a good thing to do, the last 25 years it seemed to be working pretty well, so that's what we'll do before we try something else. So this taken together is what will be the overall topic of the course. And your particular learning goals will be developing those requirements. First of all, that means finding out what those requirements are. So that means, in another term, eliciting them. This is also very typical for requirements engineering. We usually have a bunch of synonym things that almost mean the same thing, but not quite. So sometimes we have to differentiate, and sometimes we say, well, yeah, it's kind of synonym, it's pretty much the same. For example, quality requirements and non-functional requirements. Some of you may have heard that term before. It is pretty close. Non-functional classifies anything that is not concerned with a particular feature in a system. A quality requirement is a subcategory of that. That talks about the performance of a system, the robustness, the reliability. But that is a subchapter we'll talk about later. Back to the learning goals. So we're going to develop requirements. We're going to learn a number of techniques of how to do that. We can do that in the form of natural language requirements. And we can do that in the form of modeled requirements. And modeled or model-based requirements, that can be some form of graphs, some form of formulas, and some form of code or pseudocode. Many of these graphs you may be familiar with. Some of those are UML diagrams. For example, UML diagrams. Formulas are more mathematical representation, which means they're very precise, but they can also grow really complex and really complicated. So this is what we often use when there is a high security or safety relevance of our system. Then we want to know, we want to be able to prove that a certain requirement fulfills something, and that's why we want to be able to verify it mathematically. And then code is if we go into rapid prototyping, if we want to find out what a customer really needs, or if we have to try a couple of things out to know whether they can even work, then we'll use code. Either pseudocode or early prototype. For the graphs here and for the natural language requirements, this is where we'll spend a good part of this course. We call working with a lot of graphs, and that in combination with natural language requirements that fit these graphs, we call that artifact-based requirements engineering. Let me write that one down. What's an artifact? It's not like the thing that they found in Indiana Jones, but it means any type of documentation, any type of notation that would write down some customer requirements, any type of a code piece, or even any PowerPoint slide where some CEO of a company said, this is what we envision in the future, that may be relevant to the system you're developing for them. So that can include goals, that can include other stakeholders, and that can be information about constraints. And we will talk about what each of these three are in more detail over the next few lessons. Now, apart from learning several methods on how to develop these types of requirements, and apart from learning these concepts in detail and how we can represent them, the most important part about requirements engineering is communication. So the requirements engineer is kind of the communication gateway between the stakeholders, who are all the people who we should care about to talk to for a specific system under development. And on the other side of that communication gateway are the software developers, your designers, your quality assurance people, your testers, everything and everybody who helps get that system on the market. And the requirements engineer needs to be able to translate in between the stakeholders over here who don't necessarily have a lot of technical knowledge and the very technical people back here. So we need to be able to speak both languages, and we need to be able to translate what the non-technical people say into what the technical people can easily understand. And we need to be able to translate proposals of the technical people to the non-technical people so they can sign off on a specific set of requirements or a proposal to their solution. So this is a very generic idea of what requirements engineering is and what we'll be dealing with this semester. We'll learn how to do requirements, how to elicit and find them, how to write them down, how to document them, and then also how to prove them and how to communicate them to the stakeholders.
Recording, so whenever you're ready, go ahead.
Welcome back, requirements engineering. I wanted to give you a brief overview of the process of software engineering and where the process of requirements engineering sits in there. So when you take the overall software engineering process, we have a few phases. It starts somewhere here. Wait, yeah, first mistake. I was going to write software engineering up into this one, but that's actually the headline. So erase that, start again. So software engineering is the entire thing. Then this first part here is what we call requirements engineering. After requirements engineering, we go into design. From there, we move on into implementation. From there on into testing. And then we have deployment and installation. And finally, maintenance and evolution.
That client review was brutal.
We're gonna be underwater for weeks.
I'm already so pruny.
This is like a model of the very basic software engineering process. One of the really cool old school professors in requirements engineering, his name is Al Davis, used to say, essentially, all models are wrong, but some of them are useful. And what he means by that is that any model that we make, conceptualize, draw of something is an abstraction of the actual thing. Because if we try to represent it in all detail, then it would be so complex that it's not very helpful. So we abstract from the reality, we simplify, and that way we have an easier time to get things in our head. Now, one of the abstractions of this model is we're usually not starting from scratch completely. That may be the case sometimes, but for many of the systems that you'll be working on later, there will be previous systems that you either need to replace seamlessly, or where there has been an old system in place and now there is a significant shift in technology and you have to introduce something new. On the other end, we're also not going to end in nirvana, hopefully. There will be a continuous process, and at some point there may be a loop back here. We have to start again with requirements engineering. We've maintained the system over time, but eventually the system has been fixed and patched in so many different places that there just needs to be a significant overhaul, and then we start again over here. That is one of the simplifications. The other one is, this implies a linear process. Ain't happening. For those of you who already have a little experience, even just in developing a small app, you know that you start somewhere here, you get to a design, you start implementing, and then you're like, oh, this didn't quite work as I thought it would. Okay, so you have to go back and fix the design, and then you implement again. Or you figure out during testing, wait, this is not really doing what we said we were going to do in the requirements. Go back, fix it. Go back, talk to the stakeholder, find out what they actually needed. Fix the design, fix the implementation, back to testing. Hopefully move on into deployment. So that's the next simplification. There are actually feedback loops here that go back. But this you may already have heard of in earlier software engineering courses. In our course, we focus on requirements engineering. Now, if we take away these feedback loops, now you know that they're supposed to be there, so we'll just abstract from them. We're instead going to look in detail into what requirements engineering is, what the phases of that one are. Again, a little simplified. Requirements engineering has 4 major phases. The first one is requirements elicitation. This means I ask stakeholders for their wishes, their constraints. I find out about their needs. And then once I have all this knowledge supposedly in my head, and I'm saying supposedly because it's not as easy as go interview 3 people, come back, write everything down, and you're done. You probably have to go back a couple of times and clarify. You have to find out, oh, I also need to talk to the person over there, and I need to call that person in the other time zone. And sometimes you only find out here, oh, there was somebody else who I should have talked to here. We'll get to that problem later. So after requirements elicitation, what we do is requirements analysis. And requirements analysis is basically, I look at the set of requirements that I have written down, and I try to find out whether they fit together. Are they consistent with each other? Or are there any contradictions where one requirement says we are going to need to stay below $10,000 for the development of this product, and the other requirement says we need to have availability 24/7, which means we need at least 1 redundant server, which means we're going to run way over $10,000 budget. So we have a so-called conflict in our requirements, which means we need to go back over here, talk to stakeholders, and resolve the conflict. Next phase is requirements documentation. That means I write it up in a way that I can go back to the stakeholders and say, this is how we understood what you were telling us. Are you going to sign off on this, that we are supposed to develop the requirements on this basis? And doing that is called requirements verification and validation. Wait, now, which one is which? Verification, validation. So verifying requirements is, did I correctly write down what these people said? Validating the requirements means I go back to these people and ask them, is this what you really need? So what we use as a mnemonic for verification and validation is, verification is, am I building the system right? And validation asks, am I building the right system? So those are your 4 phases. Start with elicitation, move on into analysis, go back if there were questions open, documentation, go back if you figure out, uh-oh, that is not feasible, there are conflicts in here, or if you find you don't have enough information to properly document this. And then once you have everything written down and you think this should all be good, go back to the stakeholders and ask them if that is indeed the case. You see these arrows here are a recurring thing. And there is one more little aspect that I want to add on about arrows and recurring things. You see that all of this fits into requirements engineering. And we said from design, we often have a path where we have to go back to requirements engineering and fix something. Now, if we take all these details down here away, which the sport is a little reluctant to letting me do, then we can ask ourselves what is going to happen if on a high level and I don't even know what the requirements are going to be on a lower level. Let me give you an example for that. If I develop a new car, let's just be ambitious. We're going to develop something way cooler and better than Tesla, right? Because we have brilliant ideas and we're going to make them all come true. And while my arm is getting sore from erasing all of this, in our heads, you are coming up with the next vision of the vehicle of the future that can transport us super quick from one location to the next location, that can cook coffee at the same time and will respond to all your emails and you don't even have to navigate. So for this cool car, when you come up with your vision, then you don't necessarily know what you want the seat to look like, or you don't necessarily know yet what kind of multimedia system you want in there, or how the hood should be shaped. You may know some of these things, but not all of these things. First, you think of, I gotta try and develop a car, which means I need an engine, I need tires, seats, I need a body, and plenty of other things. So you already take a couple of early design decisions, and then you start thinking about what are the individual subsystems. So you have one system, and you develop the requirements for that system. And then you go to a first design of that system. So your system design, sorry if this turns out to be tiny writing, but it says system design, no black magic to it. It's going to have 3 subsystems because we are making a model and we're grossly oversimplifying. This is our model. This is going to be the car. Now, to understand what these subsystems need as requirements, we're going to look at each of them and perform requirements engineering again. So we're going to do requirements engineering for a subsystem. And we can repeat this process quite a few times, because for a system as complex as a complete vehicle, we're going to have quite a few levels of breaking down systems into subsystems. So this one Spectacular has 4 subsystem components. And you guessed it, we're going to do the same thing all over again. So now we're at the subsystem level. Okay, to not turn this into a bad joke, I'm not going to repeat doing this. I'm also running out of board. But you get the point. We start with system level requirements, system level design, move into the next layer, system design, move into the next layer, system design. And now I'm going to need a different color. The researcher Bashar Nushaibi, who is a professor at the Open University in Ireland, and a pretty funny guy, by the way. If you ever meet him at a conference, he does not only develop really good research, he's also a good guy to hang out with. He developed this model called Twin Peaks, which says exactly that. You start with requirements, then you'll have to do some design decisions, dig deeper into requirements, make lower level design decisions, dig some deeper into the requirements, and so on and so forth until you have your complete system specified. So that is the Twin Peaks model. And remember, it all started with those 6 very simple phases of software engineering. So depending on the simplification that you make for your model and the perspective you need to analyze, you will choose a different representation of the software engineering process. But this is how the perspectives tie in with each other. Okay.
Okay, action.
Hi, welcome back. Requirements engineering, this edition is going to be about problems and requirements engineering. You may remember from the very first video that I said, well, if people in requirements engineering don't do their job properly, we're going to run into trouble later on during software development. But I didn't quite let you in on the details of what are the things that can go wrong. So today's topic, problems in requirements engineering. The first problem and the best known problem is incomplete or hidden requirements. Now, incomplete, well, maybe we didn't ask enough questions, or they didn't remember to tell us everything. Hidden is a little bit harder. And that can be the case because sometimes things get political within a company. One unit of the company wants something different from the other unit. But these guys talk to the requirements engineers way more, and they're like, oh yeah, this other business unit, they also want that thing, but we're going to tell you what it's about. So there may be different agendas going on, and as a requirements engineer, especially if we come in from externally, we won't necessarily know about that. Second problem. We touched upon this one briefly, that's inconsistent requirements. When one requirement states something that contradicts another requirement in your set, and you cannot possibly satisfy both at the same time. A third one, very common, is terminology.
With Asana, AI teammates can help level up your goals by connecting them to relevant projects, so every team knows their role in the bigger picture. Asana, the #1 AI work management platform. Try for free today at asana.com.
If you ever think I beat you over the head with too much terminology in this course, once you've been out in the wild doing requirements engineering, you're going to become as insistent as I am with terminology. Because only because people use the same term does not necessarily mean they mean the same thing when they talk about it. Best example is throw a bunch of software engineering researchers in a room and ask them, hey, what is a system? You're going to get 25 different answers if you had 15 people in there. Now, that's ridiculously exaggerating, obviously, but you would be surprised with how different understandings people can come up for the same term. So unless you take the time and talk about what are the most important terms for this system, you may run into trouble. Another part about terminology is, as a software developer and as a requirements engineer, you may end up working in a domain that you're not very familiar with. If you are really enthusiastic about technology, you may not be very enthusiastic about insurances. However, insurance companies need a lot of software systems. So you may end up working for a software development company that develops systems for insurance companies, which means you will have to become familiar with their terminology. So it's important to either put the time in and learn about the domain yourself, or to have access to a domain expert, to a stakeholder from that company who will walk you through all the details and explain the necessary terminology to you. Fourth one, unclear responsibilities. That means it is not clear who has the say, who is allowed to state requirements. It is not clear which stakeholders are the most important ones to interview, and that can later on lead into trouble when you find out, oh, there were another bunch of people that I should have talked to, but I didn't because I didn't know. And along with unclear responsibilities, we often have communication problems. That can be the structure of communication, that can be a chain of responsibility thing, that can be people writing short emails without being very explicit in what they mean, or people communicating between separate cultures where same words, again, terminology can mean different things, or where we just have different habits of how we communicate certain things. Number 6, moving targets. Got a squeaky pen. Moving targets means my customer changed their opinion about what they wanted. Oh, but last week you said you wanted these 3 features, and now you tell me that one is not important anymore, but you want these other 2? Sure, we can do that, sir. Okay, yeah. And then you write down your requirements again, and then you're ready to start prototyping, and then they change their opinion again. Uh-oh. The problem is you are not moving forward in your development, and eventually you're going to run over budget and over time. So while this is still likely to happen, your customer may change their mind upon a specific feature at a certain point in time. You need to make sure that they sign off on the baseline requirements after a specified period of time, and that it's clear when they need to pay additional charges or when they need to pay for an extra feature. So you can avoid the costs of moving targets and running out of time. Number 7 is technically unfeasible requirements. I would love for my email client to be able to cook me coffee in the morning. That is a very silly example of a technically completely unfeasible requirement. And that one was an easy one to spot. But what if it's not that easy to spot? To be able to deal with those, you need to make sure that in every domain you're touching, you have one domain expert on your team. Which means, if we stick with that example of the insurance system, you need an insurance expert on your team, you need an expert on the type of database that you will be needing for that system, and an expert for the type of user interface that you'll be needing. And fourth, an expert on the types of algorithms that you may be needing for that system. I'm just making up in my head that we have to calculate some risks and quotes, for example. That is something that would often happen in insurance companies. A couple of more problems to go. By the way, all of these problems came out of a global study on problems in requirements engineering that we started at the Technical University of Munich about a handful of years ago now, and this effort was led by Daniel Mendes Fernandez, who used to share an office with me, and we have now replicated a survey on problems that people come across in requirements engineering in more than 15 countries across the world. And so all of what you see in this list is feedback that we've gotten from industry partners over the past few years. So we got 3 to go. Number 8, stakeholders. And the trouble with stakeholders is they're humans like we are, and they are not experts in the domain of software systems development. At least they are not usually. Which means that stakeholders don't necessarily know how to separate between what they knew as a previous solution and what is it they actually need. So Steve Jobs put that into words a few years ago, saying, well, the user doesn't know what they want until I show it to them. That was very specific to his type of work because he was making individual little consumer products that people would get excited about. So you didn't know you wanted 1,000 songs in your pocket until it was possible to have that. But even outside consumer goods, that may still happen, because if you are, say, a person working in an office and you used to file all these forms away every single day, for you it would already be a huge improvement to scan these forms and to then file them. And it doesn't even occur to you, because you don't know that type of systems yet, that you could have all these forms in a web form where you just fill in the details and then you file it away. So stakeholders don't know requirements. From previous solutions. Okay, 2 to go. Number 9, underspecified requirements. Underspecified requirements are a problem because that means I may not know for sure which one of the possible interpretations is the one that they needed. I saw a silly comic once about an underspecified requirement that said a user can only delete blog posts when they're logged in for a blog posting system. And then the mock implementation was a screen that said to the logged in user, oh, I'm sorry, you cannot create posts, you can only delete them while you're logged in, which is a blatant misinterpretation of that requirement, but it wasn't clearly specified that the user could do several things when he's logged in. Number 10, last but not least, unclear or unmeasurable non-functional requirements. Now, non-functional requirements are a topic that we will treat in more detail in a few weeks. For now, you just need to know that many of those specify certain quality characteristics of the system. Now, unclear and unmeasurable gets us into trouble, because if my requirement is the system should be fast, I say that's great, but I have no idea what fast means to that stakeholder. Fast could mean the database sends me a response within 3 seconds. That could be okay for if this is like a multimedia database and it's not super urgent. 3 seconds could cost you a few $1 million if the system is on the stock market. So you want, especially your non-functional requirements, to be very clearly measurable. So we got a list of 10 problems of requirements engineering. Luckily, over the years, we have developed some pretty good strategies of how to overcome them. It's not bulletproof, but we are trying our best. And now that you know which problems you're most likely going to run into, and we're going to talk about the strategies that you can do to prevent them, you're going to be prepared as I can get you at this point.
Okay, go ahead.
Hi everyone, we are back to requirements engineering, and today the first module we'll talk about is the general process model. So we have spoken about what the process in requirements engineering looks like, and today I want to give you a little background on when you need to develop a model for whatever development process, how you can go about this. So, topic, generic process model. And whenever we develop a process, we will usually have people involved. We need people to get things done. In order to do that more efficiently, what we want to do is assign them roles. So we want to assign them responsibilities, specific responsibilities. So one building block for our process models are roles and responsibilities.
What's up?
Hi, Jira. We brought you here today to let you know that we made the business decision to...
The second one is for these people to do anything, they will need some kind of tools. And that used to be nails and hammers in the good old days. These days it's things like databases, drawing programs, and maybe a modeling environment. So whatever tools they need, that can include things like PowerPoint or Word documents. Not endorsing any specific company, it's just because their names are so prevalent. A database or drawing tools. And there can be many more, like any type of IDE, integrated development environment, all of those. That's our second building block. But what are these people going to do with these tools? So the next part is we need to define what their work results are supposed to look like. And this is what we call artifacts. You've heard the term artifacts before. You remember they are not what Indiana Jones found in the jungle. They are more definitions of a work result. And we'll talk about them in more detail later on. The fourth block is how are these people gonna develop this using that? So the fourth part is the activities or methods. And what we get at the center is a process model. Anything missing? Let's see. These people are going to get that done going this way using those tools. All right, let's get to work. There is a thing missing. There is a thing missing. Help me. By when are they going to get done? There is one last element, and that's milestones. So this is number 5 for your timeline planning. Because the plural here, artifact, suggests that we probably need several of those. And maybe some of those are the input for later ones, and that means we need an order. And the easiest way how we can identify which of those we can develop in parallel and which of those need to be developed sequential is by defining milestones for them. So when these people know in which order they need to develop that via these steps using those tools, we're pretty good for our process model. Let's do a little example for that. Let's say we have to develop the quality requirements for our system. We're gonna assign a role for that, and that is our QA person. And the responsibility is draft quality requirements let quality requirements be reviewed and get quality requirements signed off. Those are the responsibilities. Now, how are they going to develop the quality requirements? There are several methods that we can use for that. For example, there is a framework by Professor Martin Glintz from the University of Zurich in Switzerland. He has developed an NFR framework. Sorry, NFR stands for non-functional requirements, of which the quality requirements are a part. So as a method, we're going to use the NFR framework by Martin Glintz, published at the International Conference on Requirements Engineering in 2007. This is a little forward pointer. We're going to talk about that in a few weeks. But so we have defined a method that we're going to use to develop these quality requirements. Tools. So for writing down quality requirements, there are several options. We can go for a Word document or for any type of desktop publishing document if we decide we want mainly natural language requirements. The advantage is this is pretty easy. The disadvantage is natural language text documents are a little harder to manage in the sense of if I want to sort the requirements according to priority, if I want to find the different categories, if I want to find, for example, all reliability requirements of a high priority, then that is certainly not an easy tool to use. So instead, we may want to opt for a requirements database. A very simple version for a database can even be just a spreadsheet. So simplest version that is still searchable, spreadsheet. And you would be surprised if you walked out into industry and found how many companies of a considerable size still do their requirements management just in spreadsheets. So while at some point in this course we will look at fancier database tools for requirements specifically, just know that a lot of companies work pretty well with spreadsheets. Last but not least, milestone. We already know responsibilities are get the thing drafted, get it reviewed, and then get it signed off. So we do want to define several milestones for that. Our final milestone, say, is going to be end of June. And then from there we go backwards. Needs to get signed off. The person who needs to sign off on that stuff is often gone for a few days at a time. They may or may not have good internet access. So maybe let's give it 2 weeks to get that last step done. So we need it reviewed by mid of June. And that means we need them drafted by end of May. This is a pretty high level planning. I'm telling you something like, oh, middle of that month will be fine. Usually you will just set a date. But now we're all covered for developing our quality requirements. And this model is so generic that you can plan pretty much anything with it. I'm tempted to say you can even plan your next birthday party with it. The question is that really the way you want to plan your birthday party? But you would certainly have some artifacts, like there's going to be food, there's going to be invitations, there may be a guest list, and there may be some games you want to play or something like that. And there will be activities to get to these work results. There will be roles, maybe you have a couple of helpers, and there will be tools that you use, and you need milestones to get that done. Because if you forget to invite people before the party, then not too many are going to show up. Okay, silly example, taking it pretty far. But the point I'm trying to make with that is for pretty much any process in your life, especially in your work life, you will need a process model if you want to get it done in a systematic way and if you want to be able to rely on the work results. And therefore, stick this in your back pocket. It's not only useful in requirements engineering, but all across the board.
All right.
Hi, hello everybody again. Welcome to the next chapter on requirements engineering. Today we'll talk about principles, processes, and roles. I'm happy you made the time to show up. Thank you. So let's see what we got for today. First, I'll give you a brief overview of the requirements engineering process, and then we'll look into what the typical roles in requirements engineering are and what other phases of the software engineering process requirements engineering interfaces with. And then there are two principles that I would like to talk about. There is activity orientation versus artifact orientation. That is more a paradigm of how we can choose to document requirements engineering. And then there is problem orientation versus solution orientation, which is a super important basis for whenever you get started with a new project. All right, let's dive right in. Process. The overall requirements engineering process can be
It's the Hostinger Black Friday sale. VPS hosting now from only $5.99 a month. Get epic savings for a limited time only with free weekly backups, free real-time snapshots, and NVMe SSDs. Safeguard your server and protect your data with cutting-edge security tools. And get access to expert support 24/7. Make your digital breakthrough with the biggest Black Friday sale ever. Go to Hostinger.com to claim your deal now. 3, 2, online.
depicted in a beautiful turquoise ellipse. Doesn't have to be turquoise. So we see the 4 phases. We start with elicitation to the top left, then we move on into analysis and then documentation, and then we go past validation and verification to then another circle of elicitation. So the elicitation is where we find the initial requirements, where we talk to stakeholders, where we interview, where we make surveys. The analysis part is where we look, do those requirements form a consistent baseline? Are there any contradictions in between them? Are there any trade-offs that need to be made? And then we move into documentation. So for the documentation part, we have to think about what is the right way of how to write down requirements. How can we how can we document them in models? How can we document them in, say, UML diagrams, or whichever other way is easy to understand for your main stakeholders, for example, your clients. And then finally, the validation phase is where I go back to my customer and ask them, is this what you really wanted? And on the bottom part of the slide, we see a few tools that we need to do requirements management. For example, the traceability matrix, that one keeps track of how the requirements relate to each other. And then we have a risk and status report. That one helps us to manage risks over time, to plan the next phases of the project, and to manage any changes that come up. So we see that project management and requirements engineering are interlinked via the requirements management. For the roles and interfaces, we have a number of major roles. In the figure on the bottom, you see all the roles that have to do with web design. So not all of those are requirements engineers, but all of those would be people that if I develop a web system, we would eventually talk to. So to get started with requirements engineering, we have the person who carries out the tasks, the requirements engineer. Then we have a product owner, maybe entrepreneur, maybe a business analyst, whoever takes the position of representing what that product needs to resemble on the market or for the users, that's your product owner. And then we hopefully have a few domain experts who are very knowledgeable in the domain that we are developing the system for. So if we develop software for a financial institution, we would talk to a finance analyst. If we develop software for a little gaming app, then we would talk to a few gaming experts. And then there is the architect, the software architect, who is going to be the lead during the design phase of the project. And there is testing. And the testers need to use the requirements to develop their test cases to then be able to check whether the system fulfills those requirements. So both of those, the architect and the tester, are from later phases during the development process, and they both need to be talked to. The interfaces are not only other requirements engineering, other software development phases, but also a lot of project management tasks. For example, budget calculation. We, as requirements engineers, have a good overview of the scope of the project, and therefore we need to talk to budget calculation to figure out what the right frame of the budget would be. And then we need to talk to the project planners to be able to schedule releases and test plans, because again, requirements engineers have a good overview of the scope of the project, and therefore they should be involved in the project outlining. Requirements engineers are also responsible for the coordination between stakeholders. So we need to be the ones who talk to the customer, the users, the developer, and we are also involved in contract negotiation and assignment, because the contract describes the scope of the project that needs to be completed. Further on, design, implementation, and integration are the phases that follow requirements engineering. So we need to talk to the designers and get them on the right path, make sure that the requirements that we deliver to them are unambiguous and easy to understand. And then we have the verification and acceptance phases. So that part needs a test specification, and that needs to be done within quality assurance. We have a system or user documentation that we need to develop, and that is also done based on requirements documents. And finally, we evolve the project in further development. So those are all the interfaces that we may have to deal with at some point as requirements engineers. Now, if we wanted to set up a requirements engineering process model from scratch, how would we do that? We now have a rough understanding of what the process looks like. We know there is elicitation, analysis, documentation, validation, and verification, and we know there is management. But what else do we need to get this process model off the ground? How do we get started? What do we need in order to define how to organize and perform requirements engineering? So the process model that I'll present to you on the next slide actually works for any other process, for any process out there. It's a generic process model. And here it is. There are 5 elements that we need in any given process. We need the activities that need to be conducted, the tasks. We need the artifacts that come out at the very end, the work products. We need to know the roles, who are the people who are going to be involved, and we need the tools that will help us create the artifacts. And to not get off track with our timing, we need the milestones. So when do specific work products need to be ready? And on the basis of that, we can develop a process model for whatever kind of process. You will find this useful all across software engineering and even beyond software engineering for any business process that you want to guide. To the principles, we got 2 principles. The first one is activity orientation versus artifact orientation. And when we come into a company and we find that they have a whole very detailed descriptive list of what you should do, one thing after the other, then you can very easily follow those steps. But unless they also describe very precisely what the work product looks like that comes out at the very end, those work products may be of lower quality. Activity-oriented process models are very helpful when somebody is new, when somebody has never done the process and doesn't know which steps to follow one after the other. When I have a more experienced user or a more experienced engineer, they may prefer artifact orientation, because the questions that this one answers is, what do the work products look like that I'm developing within this project? So I define the artifacts that come out of it, and I then describe for each artifact the task of how this is going to go. So there is a higher learning curve because we need to be able to think in processes, but it has very clear responsibilities and it scales really well. And that way we'd have consistent terminology across all projects. So comparing the two, they both have pretty much the same contents, but for activity orientation, the focus is on the methods of how we're going to do something with the output of the work product. And for the artifact orientation, the emphasis, the focus is on the artifacts and their interdependencies. And then I also describe how to get there.
Jira is now for all teams. Even those cross-functional super teams that keep project managers up at night. With everyone cruising on the same page, tracking and reporting progress has never been easier. And better visibility means better planning, better research.
So depending on how experienced your team is and how complex your project is, you may choose one over the other. Next principle, problem orientation versus solution orientation. Solution orientation means that your customer proposes a solution or tries to propose a solution instead of describing the problem that they're dealing with. And then the developer starts implementing right away because the customer said exactly what they wanted. Great. That gets us through the project quicker, right? However, there are a couple of dangers. So the first one is we could be developing a suboptimal solution because our customer may not always be the best judge in what's the best solution for their problem. Then, even further than suboptimal, there may be a complete mismatch between the solution and the problem. And third, we could be working around instead of actually solving the problem. So instead, as requirements engineers, we really want to focus on the problem first, before starting to think about solutions. And that means that I am in the problem domain and I explore the problem domain, making a context specification, and then describing some requirements that talk about what the system should be doing in the future, but not how. Only once I start describing the how in the system specification, I move on into the solution space. And then from there on, I move on into the implementation. So the straight line indicates a traditional waterfall process, which is useful for describing what happens one thing after the other. But the truth is that we will be going back and forth in between problem and solution space. So we want to start in the problem space for sure, but we will probably make the one or the other technological decision pretty early on, and then based on that early design decision, explore the requirements further for that particular technology choice. A different view on problem versus solution is when you have a context layer on top and you first only talk about the contents and the context. So you talk about the stakeholders, you talk about the business processes, and about some external systems that are involved. And then on a second level, you move into the requirements specification level, where you talk about the system as a black box. So you already talk about what the system is going to do, your requirements for the system, but you don't talk yet about how the system is going to do those. And then on the third level, the system level, which is clearly the solution space, we have a detailed understanding of how the system is going to accomplish something. So what you see right in front of you is a very simple artifact model. It says we'll have a stakeholder model, we'll have a business process model, we'll have external systems, we'll find some way to write down the usage model, usually that's use cases, for example in UML, and then we see something that says modes, which denotes what are the states of the system, and then a functional hierarchy, so what are the features of that system. And then we move on to the more fine-grained behavioral specification and the component design. Now, why is that so important? Solution space comes way after exploring the problem space. If you remember, last week we talked about what are the most important challenges in requirements engineering, like what are the things that practice is grappling with, that industry is grappling with. And you see, if you go to the bottom of this list, separation of requirements from known solutions. So separating requirements from known solutions is something that has been reported as a problem very often. It's not always the cause for a project fail, but it has been reported very frequently. So that means it's probably delaying the process. It's probably leading to some mismatches, to some suboptimal solution, even if not a complete failure of a project. So therefore, always explore the problem space first, dig into the problem, understand what your customer is really struggling with. Don't try to just implement the solution that seems obvious. First, make sure you really understand what the different aspects of the problem are, and then start thinking about what different options there may be to solving your customer's problem. All right, hope this was helpful for you. Thanks, and see you soon. Hi again. Welcome back everyone to Requirements Engineering. Thank you for taking the time. Today we'll talk about frameworks, templates, and standards. So first, I'm going to explain to you what a framework is in general, and then we will talk about a few examples for standards. So, a framework in general is any generic means of structuring and organizing information. That means whenever you have used and structured and organized information in your life, you have used some kind of framework, whether that is in the sense of a shopping list and writing it down in categories, or whether that is in the sense of writing down an inventory, making a budget, whatever means of information you wanted to classify, you had some kind of framework to do this. Now for requirements, there are different levels. We can start from a very simple.
In the face of evolving threats, protect every user journey. Introducing the HID
requirements template for a single sentence, to something that has more contextual information, to something that has a framework for an entire specification. And we'll walk through those three stages. So first one, for an individual sentence, here's an example. The sentence template looks, as you can see on the slide, first there is a when condition, if there is a specific event that triggers your requirement, and then under what conditions are there any specific states that your system needs to be in order for that requirement even to be of relevance. And then we add a part where we say the system shall, should, or will, which states that the system is the actor in that case and how it should respond. And then we will introduce some word instead of process that will be more specific in terms of what is going to happen. And then we'll specify the things to be processed, the objects in this case. And then we may add on some more process details, maybe several of them. That's what the star indicates. And with that sentence template, we can make very specific and very clear what the system should do under specific circumstances. The downside is we can't add a lot of contextual information. We don't know who wrote the requirement, we don't know when it was recorded, we don't know what the rationale behind it was. We have just an individual, unambiguous requirement. To have unambiguous requirements, that's a pretty good thing. That's really big. But we do want more contextual information in some cases. So, problem here, missing contextual information. This is solved by templates like the Volera template. We have more detail, more attributes, more characteristics about individual requirements. So we know this requirement has an ID number, it's a type, and it refers to a certain event. We have a description for the requirement. The product shall record all the roads that have been treated. We have a rationale behind the requirement, that is, to be able to schedule untreated roads and highlight potential danger. We have somebody who authored this requirement or a stakeholder who issued it, in this case called the originator, Arnold Snow, the chief engineer. We also have something called a fit criterion. And the fit criterion is essentially how are we going to know when this requirement has been fulfilled? How can we test it? So the fit criterion to check whether this has been fulfilled is that the recorded treated roads shall agree with the driver's road treatment logs and shall be up to date within 30 minutes of the completion of the road's treatment. And then we see two customer satisfaction and dissatisfaction levels. Now we may be wondering why they have different levels for satisfaction and dissatisfaction. Shouldn't they be at the same level? No. The reason for that is if a requirement is very fundamental to the system, then the customer will expect that to be fulfilled. So if the satisfaction level in this case is only 3, whereas the dissatisfaction level is 5, that means it's a fundamental, very central requirement for the system. The customer expects it to be fulfilled and he will be highly dissatisfied, or she, if it does not get fulfilled. On the other hand, if we were to make up a nice-to-have requirement, then the satisfaction level may be very high because the customer says, oh, how wonderful that you even implemented this, but the dissatisfaction level would be low in case it does not get accomplished because it was not a very fundamental requirement. And furthermore, what the Volera template enables us to do is to list dependencies. So we know in this case, all requirements using road and scheduling data are dependent on this requirement. We also have a feeling that it would be better to include the numbers of those requirements as opposed to a generic phrasing which requirements are being referred to. But for the sake of only having this one example, we'll let them get away with it. And we have one requirement that this conflicts with, and that's requirement number 105. We also see that we have further supporting materials, namely the work context diagram and the terms definitions in section 5. If you recall from the lecture on challenges, disagreement on vocabulary or missing agreement on terminology is one of the top 5 problems in requirements engineering. So this one has been solved in section 5 of the document. And we do have a history, so we know that this requirement was created on February 29th in 2010. While this is a rather simple template, it gives us a lot of contextual information that we may want to make use of at some point, and it is a standard that is used a lot across industries. I've seen it in many different domains. We are still at the level of individual requirements. We've solved the problem that we had about the missing contextual information from the simple requirements template, but we still don't know what would be a bigger framework for an entire requirement specification. And that's what we'll look at on the next slide. Before that, we'll take 1 minute time out for a discussion. So I want you to take a minute and reflect on what frameworks you have used in the past. So yes, spend a few seconds on what frameworks have I used to write down my shopping lists and organize my personal information, but also what kind of other frameworks have you come across in your professional setting for making budget calculations, for structuring supply chain information, for structuring stakeholders, any types of structuring mechanisms, for structuring code or test cases. How were those organized and what did they provide? That may also give you an idea of what you would want from a requirements engineering framework. After that, come back and watch the next slide with me. So, one of the two standards that we'll briefly talk about today is the IEEE 830. IEEE 830, you see it comes with 1998 behind it, which means this version is from 1998. So it's been around for quite a while, and it is a document template for software requirement specifications. I'll already tell you, this one has been superseded by now, but it's still fairly in use, and therefore I wanted to introduce it to you. So the first part of the table of contents is an introduction where the purpose and scope of a system are delineated, and then a section on definitions, acronyms, and abbreviations, as well as some references and a general overview of the system. In section 2, we get to the overall description, which includes a product perspective, the product functions or features, specific user characteristics, so we'll get to know our user groups, and then any system constraints that we may have, for example, from other systems that our system interacts with, and assumptions and dependencies that we have to know to be able to develop the system. The third section is concerned with specific requirements. So this is the largest section of your software requirement specification, and it will be organized according to what type of system you are developing. So there may be a fair difference in between developing a specification for a business information system versus an embedded system. So that's why they stayed on a higher level of granularity here. And then at the end, we'll have supporting information like the table of contents, the index, and some appendices. For example, on specific input and output formats, the technical background of some components used in there, or a description of the problem to be solved by the software if that was not detailed enough in the introduction. As I said, this one has been superseded, but it's still in use a lot, so it's good to know it. It has been superseded by the international standard 29148. It's the standard in the systems and software engineering family on lifecycle processes, more specifically, the one about requirements engineering. This edition has been published in 2011. So it replaces the 830 standard, and it also replaces 1233 and 1362. The standard contains provisions for the processes and products related to the engineering of requirements for systems and software products and services throughout their entire life cycle, not only during initial development. So this life cycle perspective is something that has been added on and is very valuable, because by now all the systems that we develop tend to be around for a long time. It defines the construct of a good requirement. It also gives us knowledge about additional attributes and characteristics that we should know about a requirement, and it discusses the iterative and recursive application of requirements processes throughout the entire lifecycle. The standard also provides guidance in the application of requirements engineering and management processes for any activities that are related to requirements engineering. And for that, they also refer to further standards to the 12207 and 15288. The information items applicable to the engineering of requirements and their contents are all defined in the standard. And the content can be added to the existing set of related lifecycle processes that are defined in those other two standards, or it can also be used independently. In this course, we'll only use it independently. A brief overview of the table of contents starts with the scope of the entire standard, and then it explains which other standards it conforms to and includes some normative references. And then we have a clarification of terminology, which is really valuable whenever we want to set up new requirements engineering processes in a company. So it includes a clarification of the concepts and then also of all processes. We have an explanation of all the information items that we may come across in a requirement specification or that we should consider including in a requirement specification, and what the content of each of those items is. And then we have a couple of additional annexes for further details. So that's what I want you to look into. I'm providing a link to the specification, to the standard, and look into it, go through at least the most important terms and concepts, and think about which of those definitions you have seen in other contexts and maybe in related disciplines, and think about whether they differ in any of their explanation of the terminology. Thank you for listening.
To Zuit's future boot campers or those na katulad ko na senior high school graduate na wanted to try the...
Okay, action.
Hi, welcome back. So, today we'll talk about the principle of artifact orientation in requirements engineering. Sounds very philosophical, sounds very abstract, is not that bad. In general, there are two paradigms in requirements engineering that we can follow. One is an activity-oriented paradigm, and the other one is an artifact-oriented paradigm. The main difference between the two is that with an activity-oriented paradigm, I will follow a set of guidelines in a more or less sequential order, and I will do the tasks that the guideline tells me to do. This is how many companies operate in their process descriptions. So they will have a manual for, this is how we do requirements engineering in this company. First of all, I gotta say, it's a good thing if they have such a guideline, if they don't just wing it. So kudos for taking that big first step. Now, research over the past 15 years has shown that it is often more beneficial to go with an artifact-oriented paradigm. And what that means is I try to focus on the work results as opposed to on the activities that will get us there. So to give you a simple example, I can have, say, 3 parts in my, or 3 tasks in my list for activity orientation. Oops. Typo on the glass, not good, smears all over the place. Okay, activity orientation. This one would say, develop list of stakeholders. Elicit goals. And draft use cases. And we'll talk about these items in more detail later on. So for now, we just know stakeholders are the people who are concerned with what we have to do in this project. what they have is goals, so they have goals for that system. And the use cases are how we describe the interaction between that future system that we're building and the user. Now our activity orientation, tongue twister, says we're just going to do those 3 steps and we're good. The challenge is we don't know what the end result's going to look like. It sometimes reminds me a little bit of giving class assignments. Like, I could give you a description of, please develop a list of stakeholders for me. And you will probably ask back, well, what do you want that list to look like? So it's the same thing that practitioners ask back when they would get such a guideline in practice. So artifact orientation takes this and says, we're going to need a stakeholder model which means we're going to have a UML hierarchy of actors. And this person obviously is the boss of that person and that person, at least they're higher in the pecking hierarchy. And that person has a team working with them, and they all have their hands up because they're so happy. No, that's the UML standard. I don't know who came up with that. And this one is the rebel, he has the hands down. So this is the hierarchy, and then we'll have a stakeholder matrix that says for every stakeholder what characteristics they have. So what is their main need? What is their priority? So how important are they? And how to communicate with them. Are they right in the next office? Are they on a different continent? So that's what our artifact for the stakeholder model would look like. Now, if I did not give you any instructions on how to fill this out, and if you did not get any more information on how to develop a list of stakeholders, which one do you think may provide you with a better guidance on this is what your boss wants to see at the end of the day? A lot of companies think this one. And so we do the same thing for the goal model. And the goal model will have some business goals that get decomposed in some usage goals that get decomposed in some system goals. And I'm going to explain all these terms in future modules, so don't worry about the individual terms right now. I just want to point out to you that when we emphasize the work results over the process of how to get there, we are more likely to be able to assign different responsibilities to different people and then plug those modules together into one consistent requirement specification. For the use cases, we're going to need those here as input. So they're going to be developed third in a use case model. And for a use case model, we have a little use case overview diagram, which we're also going to talk about in more detail in the future. And in each of those scenarios gets described in a textual template. Now, what I want you to take away from this is not so much the term of artifact orientation and you carrying that into your future company saying, oh, you're still working activity oriented, we need to shift to artifact orientation. No, not necessarily. What I do want to point out to you and what I think is the important point for you to take away is that when you come into a company and you see a process guideline that gives you a very detailed description of the steps that you're supposed to take, but that does not define what the work results are supposed to look like, then you want to point that out and you want to Make sure that you sit down together and you develop a template of what these work results are supposed to look like. And yes, depending on different types of systems, they may look slightly different, but you can develop a baseline template and then adapt it as needed for your specific project. Hi everyone, welcome back to Requirements Engineering. Today we'll talk about business case analysis. So, from previous discussions that we've had, we know that a business case analysis is usually something that comes in as an input for our work. First point today, why do we even talk about this? Then what is a business case? How do I write one? What are the individual elements for it? And what tools are available to help me out in doing this? First of all, why? Rudyard Kipling said, "I keep 6 honest serving men. They taught me all I knew. Their names are what and why and when, and how and where and who." So that gentleman was an English story writer, poet, and novelist, and he was born in Mumbai and he moved to London, and he did a lot of tales and poems of British soldiers in India. And my personal favorite that this gentleman authored was The Jungle Book. Anyways, he tells us how important it is to always question the why and to learn more about a specific context. So a business case is an argument, usually in a documented form, that is intended to convince a decision maker to approve some kind of action. And the document itself is sometimes also referred to as a business case. Now, the analysis process that we have to follow through for this is to start with some kind of preliminary business case decision based on the knowledge that was available, and then decide, do we know enough? If the answer is yes, then we try to move on to the final judgment, and then finalize the charter, complete the project, and end the project. If we know enough to move forward with it, then we can go to a tentative charter for, say, the next stage of the project, for a project increment. And every time new information comes in, we add it to the available knowledge and then make another tentative charter. Or when we have sufficient information for the final decision on the project, we move on into finalized charter and completing the project. The format of a business case is to help us understand what's the problem we're trying to solve, and then describe a couple of solution opportunities. How can we address that problem? And then to describe the approach. What are viable solutions and viable options to implement a solution? We also have to talk about the risks associated with each of those project options. And what's the risk if we don't do anything? So business as usual, do nothing, is always one of the alternatives that you want to talk about in your business case solutions part. And in the end, what's the value analysis? How are we generating business value from each of those options? And based on that, we can decide which option we're going to go for. The business case analysis document is often structured in the 7 sections you can see here on the slide. The executive summary, problem statement, analysis, solution options, project description, cost-benefit analysis, and recommendations. In the following, we'll look into each of those sections.
Meet Claire. Claire uses Asana, a work management platform, to get more done and save.
The executive summary is a high-level view of the business case document. It is represented in a very condensed form in plain language. The content of the executive summary is the problem that the proposed project is intending to solve, major considerations that were taken, the resources that we require to complete the project, the desired outcome, predicted return on investment, and a projection of by when that return on investment should be achieved in the future. Now, careful. You know, anytime you write an executive summary, a lot of people who get a hold of this document may read only the executive summary. So it's really crucial to include the most important bits and pieces of information here. Everything that is essential to an informed decision. if your manager ends up only reading the executive summary, you still want them to take the best decision based on your analysis. And with regards to the order, like the abstract of an academic article, we present that executive summary first, but of course we have to do the analysis first, and then after the rest of the document is completed, we improve that executive summary. So we may draft it early on, but we certainly need to revise it at the very end. It's kind of the business card for the rest of your document. Next part is the problem statement. It's a straightforward articulation of the problem that the project is supposed to solve. And it identifies the area or areas where there are issues that need to be addressed, such as some inefficiencies or some opportunities that we may have missed in the market, some unacceptable market performance, maybe in a specific niche, or unfavorable customer response or consumer response to a product or service. In the analysis, the third part, we try to explore the situation behind the problem in more detail. So we try to understand how we got into that problematic situation in the first place. What was missed before? What was the information that we failed to see, or the development that we failed to recognize? We also include some general projections about potential events if the current situation continues. So if we assume we're not going to change anything what we're doing, what does that mean in the future? Does that mean we're just going to not increase our growth? Does that mean that we're going to lose market shares? Does that mean we're going to be out of business pretty soon? What is the extrapolation? And then the conclusion of the analysis should naturally lead to the next section. For doing a good analysis, we need some tools. So what are the tools that we can use? An obvious one is any business information websites and data services, like the Security and Exchange Commission, or Hoover's, or NASDAQ and Dow Jones. Then we have news sites like the Wall Street Journal, Business Week, Fortune, Money. We have CNN, New York Times, LA Times, and so on. Search engines. Yes, plenty of alternatives. Lycos has the advantage of having a highly customizable search with Boolean terms. Alta Vista scores higher with keywords early in a document. Excite matches synonyms for you, and Yahoo has a catalog created from submissions by the actual authors. And then there's the ever-present Google. I just wanted to point out to you that they're not the only ones that you may want to use, depending on what type of search result you're looking for. And then individual company web pages that may have some good news sites, maybe some news that your customer has forgot to tell you, maybe some annual reports that we could look into and learn more about the background of the business. So make use of all of those analysis tools. Now, there is a lot of number crunching to be done when we do that analysis. We try to reveal the data by background research and then develop some charts, tables, and graphs to support our statements and extrapolations into the future. But we gotta be careful with internet resources. Winston Churchill said, "Do not trust any statistics you did not fake yourself." And what he meant to say by that is not necessarily that everybody out there is a liar, but more that you can present information in a very compelling way to suggest one interpretation over another. So data often allows for different interpretations. And we can see that in the following example. Yes, this is from XKCD. And they posted this beautiful comic on cell phones and cancer. Another huge study found no evidence that cell phones cause cancer. What was the WHO thinking, World Health Organization? Well, I think they just got it backwards. Huh? Well, take a look. And then you see this graph in the middle that says, in the United States, we have total cancer incidence rising spectacularly around the 80s, early 80s, mid 80s, into the 90s, and then kind of staying the same or even decreasing a tad. And then we have the number of cell phone users going up like crazy from about 1990 onwards. You're not there. There are so many problems with that statistic. Well, just to be safe, until I see more data, I'm going to assume that cancer causes cell phones. Okay, I guess most of us know that that isn't true, but it is an example that illustrates really nicely how we can interpret data the wrong way. So what we see here is a correlation, but not a causation. The next section in our business case are the solution options. So as we see in the top right corner, problem, need, mission, filtered with constraints into a vision can then be implemented by certain solution options. So in this overview graph, if we ask how, we go from the top level to the bottom. And when we ask why, we want to be able to trace back from the solution options to the vision and to the problem. So in our solution options part, we try to identify potential solutions to the problem and describe them in sufficient detail so the reader can understand them. So if, for example, the solution proposed is the implementation of desktop virtualization, you would define the term and discuss the use of technology within your industry. And for most problems out there are multiple solutions possible. So you should explore all the solutions that are potentially the best option. Why? Isn't that a whole lot more work? Well, if your business case analysis lands on the desk of a manager and they quickly flick through it and they're like, well, did you also think about that solution? And then they don't take a decision. So you want to show them that you did your homework, you considered all possible options for a solution, and drew the conclusions from that. Fifth part is the project description. So in this section, we describe the project, including all resources that are required for its implementation. That also means the project budget and a timeline with measurable goals for the project milestones. Otherwise, we won't know if we have the milestones achieved. And we also want to list any assumptions that the reader should be aware of. For example, that government regulations pertinent to the project won't change. Because there could be changes in the law. But if we have to make assumptions about that, then our scope changes potentially a lot. So that may be too much to pack into one document. You should also list any dependencies, like the completion of other projects or the availability of key individuals or stakeholders or domain experts that you need to realize it. And note that any risks involved with the project and briefly sketch out a plan of how you would deal with them if they come into existence. In the budget section, we want to have financial projections for the most relevant metrics. The most relevant one is always the return on investment in an economic company and the total cost of ownership. Also, project potential scope creep, often an additional 15 to 20%. Last but not least, identify and describe all the stages of the project, which includes a post-project review. So include measurable criteria that we can, at the end of the day, determine the success of the project. Number 6, cost-benefit analysis. So in that section, we want to figure out for all the options, including the proposed solution, and the most likely alternatives, which are the costs and the benefits. The likely alternatives also include don't taking action at all. Try to illustrate your case with data from similar projects and case studies if that is at all possible. We often have charts and graphs in this section that make it easier to understand what the trade-offs are, but you could also stick them into an appendix at the very end of the document. In any case, graphs can illustrate points that are hard to understand from just narrated text. So most of the time, having a couple of well-visualized graphs in there is very helpful. We also want the projected financial benefits to the company in there and a projection of when the payoff is expected, as well as an overview of the major risks to success. Last but not least, recommendations. So in this section, we make the overall recommendation for the project and how it's to be conducted. It's a brief statement of what the compelling results are going to be of the cost-benefit analysis, and then a final statement that this is how you believe the project should be going ahead. You also want to articulate the circumstances under which it should be undertaken, like referring to some key stakeholders, referring to some key actions, and include a recommendation for scheduled re-examination. If there is any question for the availability of some of the key resources, make that very clear here. And the recommendation for scheduled re-examination should happen on a regular basis. Finally, refer the reader back to any relevant document sections and the graphical representations where that may be helpful. Because the second version of speed reading, after I'm only going to read the executive summary, is to read the executive summary and then the recommendations. So that's why you want to refer people back to the most relevant graphs. Now, just to give you a first taste, a couple of mini examples. One is for Tablets for Health Systems, Mobilizing High Quality Care by Intel. And the other one is a digital signage study, Proof of Performance in Digital Signage by On Campus Media. Ask yourself two questions. What kind of business case analysis can we find online and in print media? And what do we need to be careful about when we look at those? First one, example for Tablets for Health Systems. So here we have a hospital in the Balearian Islands, like Mallorca or Menorca, and they use tablets to tell us how much better they can take better of their patients this way. It shows the company background, a little bit of the challenge, then the solution to this, and it presents the benefits. Anything missing? What are the risks? So it presents only the good side of this case. Second example, digital signage case study. Proof of performance in digital signage. Return on investment for advertisers. So if we do digital signage, how can companies make the most money with this? And here on the right-hand side, we have a couple of happy employees or happy company representatives that want to testify to the main advantages of this way of doing advertising. Again, what's the downside? We don't know. They don't quite tell us. We do see a couple of recommendations. This is how you're best going to make use of this. They do even tell us how to measure it with the measurability challenge and provide us with some data that seems to suggest that this is a good way to go, but we're not that sure about the risks. Now, at the very end, your checklist for any business case that you want to write in the future is you want to see whether your problem statement follows naturally from the analysis of the situation. And then, does the problem statement clearly indicate that action needs to be taken? Is the list of the potential solutions to the problem adequate, or is it missing any solutions that could also be a really good way to go? Is the project description detailed enough, or is it like step 1, step 2, miracle, profit? Are the data and calculations in the budget section correct? Do we have enough supporting data in the cost-benefit analysis? And have we approached at least one major stakeholder for preliminary support? And finally, it's first page, but written last, does the executive summary include all the essential elements to follow the same order as the complete document, so that your decision maker takes the right decision at the very end? Here we see a couple of website references for more examples on business case studies. And last but not least, a couple of references if you want to follow up on this in more detail. Thank you so much for taking the time. After the business case, I would like to say it's the after party. Business analyst is going to the after party because their work is done. But as a requirements engineer, that's usually where we start working. So in your work, you might be more likely to understand a business case as opposed to writing one and to then develop the vision based on that business case. So a good business case is the foundation for developing a good requirement specification. And the more you get to talk to your business analyst, the better. If you get a business case document that's well written, that's great. If you get to talk to the analysts themselves, even better. That's it for today. Thank you so much.
Let's do it.
Hi, welcome back. So today it is another little module in requirements engineering, and the principle we talk about is problem orientation versus solution orientation. So in requirements engineering, we know we want to develop a very first rough idea of what the solution is going to look like. However, we often take shortcuts or don't dig deep enough into the problem that we're trying to solve. And that has led to numerous software project failures in the past, software projects that have run over time and over budget, simply because they did not take the time to really analyze the problem in depth.
What's up?
Hi, Jira. We brought you here today to let you know that we made the business decision to switch to ClickUp. Your performance has been decreasing over the last few quarters. There's no innovation.
So when we develop a software system, we start on a very high level. We try to figure out who are the people that we even need to talk to. That's what we call the stakeholders. So we're going to start with the stakeholders. Then these stakeholders will have some kind of process that they're looking at, that they want to improve. This piece. It's a business process. That business process can be something like ordering a book online, or it can be getting into a carpool system and ordering a carpool, or it could be, I want that little robot that goes clean my house for me. Whatever it is. The third part that we need, that is already there, that we can analyze, are the other external systems. Sometimes these are connected, and sometimes they're just connected to my system under development. So here are the external systems. And all of this is the first layer. This is the so-called business process layer. And we're going to get to 3 layers today. The reason why we use these layers is that on every layer we abstract from a problem. So right now we're looking at the problem domain. We're looking at what is already there if I haven't even started thinking about my new future system. So I look at who are the people who I need to talk to that are there already. Maybe some of these people are also concerned with those systems over here, with the external systems. And I can look into those and see what is it that is currently in operation and what my system will have to work with in the future. And the third part is the business process that these stakeholders want to improve by the system that we're developing. So that business process is already there without my system being yet in place, like some previous form of it. Like even say, rewind a few years, there is not a single car sharing system on the market, but there were people figuring out how to get a ride together to, I don't know, carpool to work, or to carpool to a concert in the evening. So the process idea is there. We want to develop a better solution for it. And what we abstract from on this level is the problem of how are we going to have that done by a system. Now, for getting closer to what a solution may look like, we look at the usage process layer. And this means I start thinking about who are my future user groups? And in what way, in which ways, will they be interacting with my future system? So this is my future system under development. But I will only look at that system black box. That means that I know my user will want to do a specific task with that system. Probably several of them. And then there may be another user group who is also interested in task 2, but who is unlikely to ever perform task 1. But they need a task 3. Now, to stick with that carpooling system, those two user groups may be users who have a car and users who do not have a car. So the user who has a car, they will want to be able to offer rides in their car in that system. And the user who does not have a car will want to post, I'm looking for a ride to San Francisco next Friday, and then see whether they can find a match. And task 2 is agree on a pickup time and date. That will be something that both of those users need access to. So on this level, we talk about what the interaction between the user groups and the system under development looks like. But we do not talk about what that looks like system internally. This is just a black box. We know what it does. We don't know yet how it's going to do that. The other part that we have to look at on this level is with what quality can we provide the service? So we're going to have the quality requirements. And maybe also a couple of system constraints. Oh, typo. You're supposed to be the other way around. Okay. And both of these are subcategories of non-functional requirements. So the quality requirements say things like the database needs to respond within 2 seconds. The system should be highly reliable. And the system constraints, they make assurances about what we will need once we get to the next layer down here for the system to work as specified. So the final and third layer is the system layer. Some call it the technical system layer, so let's put that in parentheses. And this is where we say, well, how are we going to realize all of these tasks? So we're going to break down the tasks into logical components that will reside in that system. We have kind of a structure in here. So we have a component model. And we have, on a more detailed level, our system constraints and quality requirements refined .
Hi everyone, we're here in British Columbia, Canada, and we're here to share with
And we will have a first idea of what hardware components we're going to need. So this is a logical component model. And these are hardware components. So we already know we will need a physical database. We already know we will need a couple of sensors if we want to integrate that carpooling system with the online system, and we will need something like a web server, and then we'll need client interfaces. So that is on a very generic level the contents that we will be talking about. So we start here on a very abstract level, talking about only the problem. We try to understand the problem better by talking to all the people involved, by looking at the process in detail that they want to improve, and by looking at the external systems that are already there. Once we have a really good understanding of what that problem looks like, we move on and design the user level. We ask ourselves, or ask the stakeholders, that's actually the better idea. So we start with asking ourselves as requirements engineers to come up with an early draft, and then we go back to the stakeholders and ask them, is this really what you need? What do you think about these proposals? Is that what you want your future user interaction to look like? And at the same time, we look at the quality requirements and some system constraints that may arise from them. Once we have that part done, I didn't tell you the problem yet. So the problem that we tackle on this layer is, what does the user interaction look like? The problem we still abstract from is, how is that going to be divided into hardware and software? So that's what we look at on the third layer. So here we're somewhere between problem orientation and solution orientation. And down here, we finally get to complete solution orientation, because we take these very rough early design ideas and put them into a logical component model that has the different functions in here. So to put that in the sketch as well, this one is problem oriented. And this one is somewhere in between. And this one down here is finally solution oriented. Why does this matter? It matters because I want you to take home the point that at the beginning, we really want to dig into the problem analysis. As software engineers, we tend to be solution-driven people. So we hear about the problem and we're like, all right, I already got an idea. We're going to solve this and it's going to be really cool and you're going to love the user interface, and let's get going. And that's exactly how we often end up developing a solution that is not a perfect fit for our customer. So instead, we need to rein ourselves in, we need to rein our enthusiasm in, and take the time to talk to those stakeholders, to really question them in detail, to come back with early drafts often, and then we're going to make sure we're on track and we develop the right thing on the first time. The same thing does apply for Agile. So I often get asked, well, this sounds like pretty documentation heavy and time intensive. Like, how do you apply that to Agile? You use the same thing, you just go in quicker iterations. So in Agile, you may spend 2 to 3 hours talking about this with your customer. You then go and work out these parts. In your next customer meeting, 3 to 7 days later, you are going to present this and potentially a couple of first user interface mock-ups and a first logical design. And then you get feedback from the customer. If you develop a logical design for that, that means we're assuming that your customer does have a lot of technical knowledge. That may not be the case. You may just come back with a draft of this and you develop that in the background. So same is true for Agile. We just go in quicker iterations.
In the face of evolving threats, protect every user journey. Introducing.
Okay, good.
Hi everyone, welcome back to Requirements Engineering. Today we'll talk about stakeholders. You've already heard that term a few times over the last couple of weeks. And now we're going to dig in a little more detail. Stakeholders are all the people who have an interest in the system under development. And there are 4 things that we as requirements engineer are supposed to do with stakeholders. Step number 1 is identifying them. Now, if we just start from that definition, have an interest in the system under development, that gives you a good idea of where to start. So that interest is by your client, whoever pays, then there are future user groups, what's the difference in between those? If I'm a user, am I not automatically the client? No. You don't always pay. So for example, if you think of all your social networks, you don't pay for using them. You're not the client. That means somebody else gets the benefit, somebody else gets what they want from that system, so they pay for it, you use it, you also have some benefits, but you want to keep that other aspect in mind. And you've been around long enough so you know that you are basically giving away your data. That's your way of paying for social media. And the client is the person who actually pays the developers. So you have the client, you have future user groups. Who else has an interest in the system under development? We can have active and passive interest. So active interest, client, user groups, maybe somebody who needs to maintain that system in the future. Like a DevOps team, and sorry, not the DevOps team, they're in development, but part of the DevOps team may become the maintenance team later on. But you also have passive stakeholders, and that means they don't care so much about whether your system succeeds. However, they do care about whether you stick to their rules. So this is legislation. Whether your system is going to allow to violate any trade laws, for example. So you start with identifying, and there is some help out there. There is a bunch of reference lists that will help you identify your stakeholders. So that's the most common way of how we start, and I will present one of those reference lists in the slide set. Second part, analyzing. So you want to classify your stakeholders. Sorry, I mixed it up. Analyzing is the third part. The second part is classifying. Okay, try that again. Classifying. So, classifying means you differentiate who has an active interest, who has a passive interest. You identify, are they involved, with which phase of the project are they involved? Are they involved only early on during elicitation? Are they going to be involved during detailed implementation? Are they going to be involved in later on evolution and maintenance of the system? And how influential are they? So how much weight does their word have? What is their decision competency? Third part is analyzing. Now it's good to know all our stakeholders, and it's good to understand in what relation they stand to each other. So relations between stakeholders. This is what can often make or break a project, because if there is a business unit that wants a system developed, but they need all major decisions signed off by a higher boss, and that higher boss is unfortunately constantly arguing in weekly meetings with that unit manager, that project is likely going to get in trouble, because at some point that guy will just not want to sign off on a specific budget or things like that. So it's good to know, especially if there are conflicts behind the scenes somewhere. That said, it's often hard to find out about that. So the best way to go about that is to develop really good personal relationships with your clients and with some of your future users, and especially with the decision makers in the project. It is something we tend to underestimate because we like to focus on the solution that we want to develop and do that as good as possible. It's going to be a lot easier if you have good relations with your stakeholders. The other part that we want to do in analyzing is find out what are the primary needs of all those stakeholders. The difficult part about this is that they won't necessarily tell you right up front. Either because they plain don't know what the best or what the true need is, they see a shortcoming in a current system, but they don't necessarily say what their underlying need is. So for example, somebody may state that it's not very helpful that in that system they don't see a time anywhere on the page. But if they're supposed to file away things using that system, for example, take an order, send out bills, things like that, the actual underlying need may be that they need timestamps on those files, not so much that they need to see what time it currently is. Fourth one is managing stakeholders. And that means, again, communicating, making sure they're in the loop. I'm gonna make 2 exclamation marks here because we tend to underestimate that one. It's really, really important to keep your stakeholders in the loop. So you wanna go back and send them updates, frequent updates, depending on how often you meet. Say you meet once every 2 weeks, then you wanna send them at least 1 weekly update in between, so they know where they stand. And it's important to keep them in the loop, to have their continuous approval. If they feel they are involved and they are important for you, then they will in turn be supportive of what you need from them for being able to deliver the best work product. Sounds simple, but common sense is not always common practice. That's why I stress it so much on this slide. Thank you.
Awesome.
Hi everyone. Welcome back to Requirements Engineering. Today we will have a brief intermezzo about elicitation techniques. For this, we'll first look into survey techniques, then into creativity techniques, document-centric techniques, observation techniques, and finally support techniques. Here you see a complete overview of what comprises those. So for survey techniques, we can either do interviews with experts or we can do questionnaires. For creativity techniques, we can use brainstorming, a version of which is brainstorming paradox. We can do a change of perspective, which is also called the 6 hats, because you imagine that you're wearing a different hat, either the one of the product owner or the one of the always critical person or the one of the stakeholder who wants to get the most profit out of the product. There are several hats that you can put on.
Jira is now for all teams. Even those cross-functional super teams that keep project managers up at night. With everyone cruising on the same page, tracking and reporting progress has never been easier. And better visibility means better.
Another technique is the analogy technique, which tries to make use of any analogies that you can find for particular aspects of the project, and that way get new ideas. And finally, the morphological box is another version of this in terms of giving you ideas for certain perspectives that you can use analogies for. And then we have a couple of document-centric techniques. First of all, system archaeology, which means if there is a legacy system, dig up anything and everything that is potentially related to this. Then perspective-based reading means you take on several perspectives of a user, of a quality assurance person, of a future maintainer to get the most out of what you have in front of you. And then there is requirements reuse, because maybe you're developing the 10th version of the same product and there just need to be some updates to some of the requirements. And then there's business process analysis. Business processes are often documented well, and we can make use of those documents to get a pretty good understanding of the usage processes that we'll have to support in the future. Observation techniques are mainly field observation, which is not intervening with what is going on, and apprenticing, which means I'm trying to learn what that future user needs to be able to do. And then I have a couple of support techniques like mind mapping, workshops, CRC cards, audio and video recordings, use case modeling, and prototypes. All of these can be used in combination with some of the techniques earlier on the list. The morphological box is a creativity device that gives you several options to run through a product. So when you look through the process of harvest, then you need a vegetable picking device, you need a vegetable placing device, you need a dirt sifting device, a packaging device, a method of transportation, and a power source. And now you try to fill out several options for each of those devices or techniques. Sometimes this is done by passing on the paper. So for example, I fill out option 1, and then somebody else needs to fill in option 2, and somebody else again needs to fill in option 3. This helps in case you get stuck with finding enough options yourself. In the example here on the slide, person number 4 apparently got stuck with finding further options for the dirt sifting device or the method of transportation because there are no further options given. But in the end, we end up with enough options to pick something from. And that is what goes into our concept, a pick of the best suited combination of devices and methods for our product. Another well-known technique in creativity are mind maps. Mind maps help us organize content. This is often done right after brainstorming, when I have a lot of concepts, a lot of keywords to organize. So I can use them for gaining clarity, I can use them to structure, I can make use of links, colors, and images to further enhance the illustrative purposes of the mind map, and I can just develop a personal style or a company style for them. And then we have the Osborne checklist. The Osborne checklist is a creativity technique that asks us a number of questions. So by those questions, we can gain a new perspective. We can check whether we may substitute something. Who else could do that? Where else may they want to do it? What else could they be wanting to do? Could we use another ingredient? Any other material? A different approach? Could we combine parts, units, or ideas? Could we blend 2 different ideas? Can we compromise on something in this process to make it faster, for example? Can we combine from different categories? Is there something that we can adapt? So for example, how can this product idea or plan be used differently? What uses could it be adapted to? And then we have the 3 M's: modify, magnify, or minify. We could, for example, modify the meaning, material, color, shape, or the odor. Could we magnify by adding a new ingredient? Could we make something stronger, thicker, longer, higher? Could we minimize or minify something? Can we split something up, take something out, make it lighter, lower, shorter? Can we put it to a different use? Can we find new ways to use it as is? Or can we find other uses if something is modified? And then we can always ask whether there is something to simplify or eliminate. So, is there a potential to remove something? Can we eliminate waste, reduce time or effort, maybe cut costs? And then can we rearrange something? Are there interchangeable parts, other patterns, layouts? Transposing causes and effects? Can we have changes from positives to negatives or the other way around? Can we reverse any roles in here? Can we turn it backwards or upside down? Is there anything that we can sort in a different way? So all those questions just try to give us a different perspective on something, try to help us find something that we hadn't seen before. And here are the famous 6 hats of De Bono. They come in 6 different colors. The white one is a very neutral one about data and information. So this is used to record information that is currently available, and that helps us identify further information that may be needed. Then we have a red hat. It's associated with feelings, with having intuition and emotion. And if you wear the red hat, then you're the person who wants to put forward feelings without any justification or prejudice. If you get the yellow hat, you want to have a positive view on things. You always try to look for the benefits in situations. So even in people who usually are critical, that yellow hat puts forward a positive view on the world. The other extreme is the black hat. The black hat relates to caution. It is used for very critical judgment, but you want to watch out because it's really easy to overuse that black hat. The green hat is for creative thinking and generating new ideas. So this is your creative thinking hat. Think about growth, about vegetation, about things organically morphing into something else. And the blue hat, finally, the overview hat, is about process control. It is used for thinking about thinking. So if you wear that hat, you ask for summaries, you ask for conclusions, you ask for decisions. You kind of moderate the process. So those 6 hats can be really useful if you are in a team discussion and you kind of get stuck there. You don't know how to move forward from there. Then you take on those hats to get a different perspective and to loosen things up again. So finally, the requirements elicitation techniques that you want to be kind of familiar with for this course and that we practice in this course are an as-is analysis of existing systems, an analysis of business processes, an analysis of usage scenarios, deriving requirements from goals. We'll talk about goal models next week. Interviews and workshops with stakeholders, observation of users during work in the form of site visits, questionnaires, analysis of documents, templates, prototypes, experts and expert interviews, and creativity techniques. I hope this gives you a good overview of techniques that you are able to use.
Good.
Hi, welcome back. Requirements engineering. Today it's all about goals. So, what is a goal? The definition for a goal, the simplest one that I found is it is a statement of intent. And as we do requirements engineering for software-intensive systems, those goals will have to do on some level with a system under development. Mind you, little sidetrack, you may be able to use techniques that you learn in this course in requirements engineering in all areas of your life, certainly in all areas concerning your business life. We've applied requirements engineering techniques to policy making to business case analysis to finance. It works in a lot of areas. So don't limit it to software engineering, even though for this course we focus on software engineering. Now, goals. So we have 3 major types of goals. We have business goals.
With Asana, AI teammates can help level up your goals by connecting them to relevant projects.
We have usage goals. And we have system goals. You already see there are 3 levels. Yeah, we're back to 3 levels. Now the question is, what do each of these types of goals focus on? Business goals focus on the business context of your system. So it's not so much about how the system is going to work, as opposed to what you want to achieve with that system in a larger context in the business environment. So your business goals may say something like, we want to have our return on investment, well, we want to have the development costs back in 3 months after releasing the product. And further on, we plan on earning $1 million within the first year. Clearly a business goal. This one doesn't even give us a clue. We're not going to Rio, this is return on investment. This one does not even give us a hint about what our system is about. And that is something you frequently find in business goals. They don't necessarily state something about the actual business. So let's use a second example. Something that does say what the system is going to be about. So we want to take over 30% of market for online sales, product sales. That is a pretty lofty goal. It's just an example. So we do want to do online product sales. We want to be a major competitor for Amazon, because right now they're clearly number 1. Now, after establishing the business goals with your stakeholder, you want to move on into defining the usage goals. So the usage goals, as opposed to talking about the business context, refer to impact in business context. They state what the user will want to accomplish with the system. So for example, they want to be able to buy and ship quickly and safe. And number 2, they want to be able to return products. So if you think back to the little lecture about problem orientation and solution orientation, here we are still on the problem level. We don't talk about the solution yet. On the 3rd level, for the system goals, we may have an idea of what the solution is going to look like. We are going to define some goals that are going to constrain the solution. So that may be something like uses encryption for user data. Because we said that one of the usage goals is we want to be able to buy safe, quickly and safely. So we need to be able to protect our user data. And then a second one may be for easily returning products, allow for label printing. And where we go after defining the goals on the 3 levels is into an analysis of what is the relationship between those goals. So we will start by making a hierarchy. So up here we have a business goal, and then, well, in our case we had 2. And then here we have the usage goals. And 2. So both of those are derived from that business goal number 2. We want to take over the market for online product sales. This is our overall goal model. We have one root, which is the system goal, the goal of developing that system. And then the system goal of we want to use encryption is derived from user goal 1. And number 2 is derived from usage goal 2. So we make that traceable to know at the end when we've broken down all those things and somebody asks back, is like, that encryption software module costs us so much money, like why do we even need that? I know in this example it's slightly obvious, but imagine you've broken down requirements over, say, 7 to 10 levels, and they are so fine-grained that it is not entirely obvious anymore where it came from. And then you can trace back in your goal hierarchy and say, oh, this is why we did that, and this is why we did that, and this is why we did that. So you're good. The other part why you want to analyze those goals is you want to find out whether there are any conflicts. And a very typical conflict that you may be able to detect in many goal models is the conflict in between time and quality. So you know there is this development triangle of time, cost, and quality. And conflicts are often due to that one. Now, the cynical business consultant says, time, quality, cost, pick 2. You can only have 2. But the truth is that we want to find the trade-off somewhere in the middle. So we know what is more pressing. For example, we develop the next funky little app that gets people totally addicted to their game. Maybe quality is not as important and we are willing to invest a little bit more. Like if that app crashes every once in a while, so what? It's just a game local on your phone. Cost, okay, we know that everything is about the time to market with this type of product. So we know that the emphasis is going to lie here. However, if we design an airplane instead, quality, yeah, we would rather not have that thing fall from the sky. We want to make sure that it's developed with really high quality standards, that it's absolutely safe, and for that we acknowledge that it will take more time and it will be more expensive. So depending on the type of system you develop, you know where you have to go for your trade-off. That's it for today's. That's the story about goals. Hi everyone, welcome back to Requirements Engineering. Grab a glass of water, settle in. Today we'll talk some more about goals and constraints. So we already spoke about why we need goals. Goals are important to make the direction clear of where we're heading in systems development, to make sure that our stakeholders align in what they want. And we've talked about the definitions, that goals are statements of intent, and that they usually describe some characteristics that the future system should fulfill, or some direction that we wish the business surrounding the system should head into, or they can be constraints. Today we'll dive a little deeper into what types of goals there are, into refinement and abstraction, and into how we can use goal models for analysis and quality assurance, as well as a couple of other techniques for goal modeling. So, for a start, what types of goal models do we have out there? We have goals as networks of characteristics. So, they can simply be a set of related characteristics. We can depict that in a loosely connected graph. Then we can depict them in a tree. And so the tree has the advantage over the network that we have one clear starting point up here, a root node. And then from there, we can decompose and refine and look into more details. So we have also, as in the network, a set of related characteristics of goals. And in addition, they have a hierarchical refinement relation, and on same levels, they have interdependencies. We do have a couple of techniques that help us model goal trees. Some of those are chaos. Chaos is short for keep all objectives satisfied, and this was developed by Axel van Lamsverde and colleagues. And then we have GSN, which is short for the goal structuring notation by Kelly et al. And we have I-star modeling, according to Eric Yu and colleagues. Now, when we look at the expectations that goal models create, then we can read them from the bottom up. So the leaf of a goal tree can exclusively be related to its context with regard to its satisfaction. So I look at the leaf, at what the leaf says, only in regard to the context of where it came from in that tree. And looking at requirements, I know that the leaf of a goal tree can be related to the system with regard to its satisfaction, and that I can deduct both functional and non-functional characteristics of the system. The expectations as well as the requirements can be combined into assumption guarantee pairs. So assumption guarantee specification is something we may want to use in formal verification if we have to verify that our system considers certain constraints. And we can make those assumption guarantee pairs with regard to the interface between system and context. So if I assume I get correct numbers as input, then I can guarantee that my calculation is going to be precise. That would be a little example for an assumption guarantee pair.
So what is ClickUp? ClickUp is an all-in-one productivity software where you can manage everything and any.
Now we have different types of goals. We characterize goals according to what underlying system are they referring to? Are they referring to a system model? Are they referring to a quality model? Or we can differentiate them according to the application domain, according to the characteristics of the expected system context. For example, in an embedded system domain, that would differ from a business information system context. And we can differentiate the methodical approach, for example, chaos, keep all objectives satisfied, as well as specific characteristics that can be expressed by the modeling concepts that technique allows me to use. Now on the right-hand side, you see a couple of examples for high-level goals. For example, reduce production cost or expand market. Those are business goals, high-level business goals that then need to be broken down to understand, hey, what does that mean in the context of the system that I'm developing? How do I need to understand that to be able to design that into the system? And then we have the green goals, automate generation of finance reports or increase process efficiency. Those are related to the functionality of the system, which means that I have to then think about how can I design that into the system to make sure that I live up to that. And then the blue ones are quality goals. So they are on the level of system goals. Increase performance, increase maintainability, increase security. Those are all quality attributes that I need to make sure I can actually guarantee that I build them into the system in this way. Now, if we take the example types for goals according to Lamsverde, remember he is the guy who invented chaos, keep all objectives satisfied, then we see a slightly different classification. Remember, classifications are only used in requirements engineering to help us sort things more easily. So they try to provide us with a system that helps us deal with information. So there is no final answer to which framework is the best one. So I'm going to be presenting 3 frameworks in here. We have the framework of the previous slide with quality goals, business goals, and functional goals. And then we have the Andire framework that talks about business goals, usage goals, and system goals. Different category names for almost the same thing. And we have the ones by Lamsverde here, where we have quality-related goals, which are part of non-functional goals. For example, usability, performance, security, accuracy. And an example would be for reliability, 99% of the uptime, the system reacts correctly to user queries. And then we have optimization goals, which are also known as soft goals. So if they are measurable, they talk about maximization or minimization of something. Maximize efficiency, minimize costs, increases and decreases of something. An example for that would be performance. The operating rate of the tracks between A and B is increased by 3% per year in the next 5 years. Okay. Then we have behavioral goals, also known as hard or functional goals. For example, after the interaction phase, we can have a satisfaction goal where A requests from B, and we can have an information goal where A informs B. For example, for accuracy, 280 to 300 milliseconds, the train control must be informed about the state of the level crossing. So we have an information goal and we have a satisfaction goal. So we have the satisfaction in terms of within that given time frame that must happen, and we have the information goal. Train control must be informed about what? About the state of the level crossing. And then finally we have anti-goals, also known as obstacles. These could be, for example, safety hazard or security threats. An example here would be the data loss is estimated at 5% despite backup. Not what we want, but we know that that is an obstacle that we need to take into account. Now, I would like you to just take a minute and think about examples for each of the following types. Think about a car sharing system. We've used that example in the past. Just do that in your head really quick. What are 2 quality-related goals that you can think of for a car sharing system? Availability, reliability, accuracy, billing, lots of things to think about. Or then think about optimization goals, soft goals. What are things that you want to maximize? What are things you want to minimize in that system? Third, think about behavioral goals, also known as hard or functional goals. So what are the things you want the system to accomplish for the user or to support the user in? And then finally, what are anti-goals? What are obstacles for the car sharing system? Just a little exercise to get your creative juices flowing. I'll wait for you on the next slide. Here we are. So now you have an overview over a couple of classifications for different types of goals. Now, let's look into refinement and abstraction. What do we need them for? Why are they useful concepts? We know that ideally, top-down requirements engineering would happen in the form that, based on an elicited and consolidated, general formulated set of goals, like the product must be deployable internationally, we would then in a next step define abstract requirements that are consolidated and documented. For example, the product must be deployable in third world countries. The product must be usable independent of the energy resource. Those could be two requirements that we derive from the abstract goal above. From those again, we then retrieve refined concrete requirements. The system has a dynamo that generates the necessary energy. The electric tension is at whatever it needs to be. Big surprise. Independent of the energy resource, yeah, that can mean that we just have to move our legs to get that system going. And then finally, we would determine a system specification. So we use a dynamo of the company AB. But we also know from the past weeks that RE does not always happen in a top-down form. Like, yeah, in our ideal world, we have this one customer that we talk to and they instill all of their wisdom on us, and then we can just work from there. But in practice, we learn a lot of things along the way. We have to talk to many people and we have to kind of weave the information together that we receive from them. We have to consolidate. We have to make sure that we resolve conflicts in there, that we find the trade-offs. And therefore, we also need to think about the part where we go reverse. Maybe we even have a previous system specification that we need to derive the constraints from, that we need to reverse engineer some of the constraints from. And then we go back towards the goals and see which of those goals need to be adapted. Are we still on the right track? And for that, we use the concepts of refinement and abstraction. So refinement means we drill down, add more detail. Abstraction means we look at the bigger picture. We remove details. So the abstract version, goals, they're often hard to measure. System must be deployable internationally. System must be easy to use. The development will follow a systematic process. What does that really mean? So we derive some more specific requirements. We add more detail. We refine. Now the objectives are measurable and decidable. The user interface must support the languages English, Spanish, German. Or the average inexperienced user must be able to use the function rent car within 20 seconds. It must be easy to use. Third, the process must be certified as CMMI level 3. That would certainly be one way to ensure that it's a systematic process. Now, if we do the round trip, the requirements make the satisfaction of the goals more concrete over various steps, and the goals are a justification for those more concrete requirements. What is also important is the tracing for those, because ideally the relation between goals, abstract and concrete requirements are documented in a traceable way. So if something changes at one end, I can propagate those changes through the specification in either way. So abstraction and refinement, defined. Abstraction means we ask what goals are behind the requirements, what might open up the design space. So this is taking a step back, looking at the bigger picture. Which goals are determining the currently present set of requirements? So what was the reason behind the current set of requirements? So it's always why questions. We try to retrieve application domain knowledge. In the level of abstraction, we go up. For goal refinement, in requirements decisions, so we take requirements engineering decisions, and in scoping, we ask for which tasks or functions of the system do we need requirements? So we try to detail, we drill down. For which context do we need to deduce requirements? And in the system scoping, how can the design space of the problem under consideration be technically determined? So for refinement, we always drill down. We always ask, how do we do something? For which part specifically? So keep those two in mind, because that's the way how we iterate through goal models. Now, how can we use goal models for analysis and for quality assurance? First of all, most importantly, we use them to detect goal conflicts. Low production costs, easy to use, high information security. Even if I did not put that picture in the background, we could gather that, yeah, there is a potential goal conflict. So we will have to find a middle ground. Maybe you remember the triangle of cost, quality, and time, development time, where the consultant said, pick two. So cost, quality, time, you will only ever be able to optimize for two of them if you give in for the third one. Or you try to find the perfect balance here in the middle, but perfect balance is a tough thing to achieve, so usually the trade-offs will have to be made individually. Now, to resolve goal conflicts, we will first try to make goals measurable by evaluation and by prioritization. That's how we make them comparable to each other. And then for a goal, specific threshold levels are determined as standards that can be reached. Then we prioritize the goals, and then we have to resolve them by negotiation. So first, make them measurable, give them a priority, and then resolve by negotiation. There are models out there like, for example, the Easy Win-Win model by Barry Beam that can help as negotiation tactics. And Barry Beam derived this more specifically for requirements engineering, but it came out of the Harwood Win-Win negotiations method. So even if you just look up the original Harwood Win-Win negotiation tactic, then you're already well on your way. Now, I talked a few times about chaos, keep all objectives satisfied. And this technique allows us really nicely to look at goal conflicts. So we see here a local train, and it has two top-level goals. One is serve more passengers, and the other one is minimize costs. Those two are potentially in conflict to each other. Why is that? If we break both of them down, then we see that to minimize the overall costs, we need to minimize the development costs. But to serve more passengers, we need to add new tracks, and that counterindicates minimizing the development costs. So this technique makes it very obvious and very easy to explain visually to a stakeholder where conflicts lie. Yes, it may not always be as obvious as serve more, minimize costs, but this example shows you that the technique is designed to help it make conflicts very obvious. Now, last but not least, a couple of techniques for goal modeling. I mentioned keep all objectives satisfied, and then there's also the I-STAR modeling framework, Eric Yu et al. And then we can use system dynamics and balanced scorecards for encompassing analysis and simulation of complex dynamic systems. Balanced scorecards come from the area of business analysis. So here we venture off again into the area of business analysis, which is a good thing because they are our #1 source of information. And then some of the basic ideas and commonalities of goal modeling techniques are that we have usually the possibility to hierarchically decompose goal into subgoals. We can model dependencies, for example, conflicts, but also supporting relationships. We can map goals to agents or stakeholders. So those agents can be subsystems, that can be components, they can be actors, or more high-level stakeholders. And goal modeling techniques allow us a seamless transition to design because they provide a structured way of breaking down information and refining information that will eventually feed into the design. So here again, a chaos example. In a little more detail, how we use that notation is you start with the soft goals, which are denoted by a fluffy cloud. Soft, fluffy, yep. And you can model an abstract solution alternative via an OR, and you can model a goal satisfaction via AND combination. So we can say, if we want to serve more passengers, we can either add new tracks, or we can maximize the train speed and minimize the distance between trains. Both of those are valuable solutions, or feasible solutions. And if we want to minimize the costs, then we have to minimize the development costs and also minimize operation costs. And if you remember the refinement and abstraction, if you want to go one level up, you ask why. Minimize development costs. Why? Because we want to minimize costs overall. And if you ask how, you go one level down. How can I minimize costs? By minimizing development costs or minimizing operational costs. We also have the opportunity to show positive and negative contributions, denoted by pluses and minuses. So we know that maximizing train speed and minimizing distance between trains will contribute to serving more passengers. And new tracks added will subtract or take away from minimizing development costs. We have, like I said on the slide before, the fluffy clouds denoting the software optimization goals, and the rectangular goals at the bottom, they are behavioral goals. So that's where we become really concrete, where we essentially take early design decisions on how this is going to be implemented. So we can measure the goal satisfaction by evaluating how well sub-goals and hard goals that implement your soft goals are implemented. And then we prioritize, and when we take the measurable requirements that we've broken our soft goals down into at the bottom, and then add up what they bring in terms of goal satisfaction, and we get back to the overall evaluation of goals. The other technique that is very much in use out in academia, but also to a certain extent in practice, is I-STAR. The difference of I-STAR is they focus more on modeling goals according to which actor they came from. So you see here a meeting scheduler, and the dashed lines give an actor boundary, which means this is the area that one certain stakeholder is concerned about. So on the right-hand side, we see a meeting participant who has an actor boundary around a bunch of goals, from participate in meeting to finding an agreeable meeting to agreeing on a date. So depending on whether it's more important for you to be able to model constraints and the trade-off between constraints, which would point towards chaos, or whether it's more important to you to differentiate the information sources that your goals came from, that would point more towards I-STAR. This is one way how to choose your modeling technique. Finally, the references for this one. Axel von Lambswerde wrote a pretty solid book on requirements engineering, where he describes how you get from system goals to UML models to software specifications, and he uses the chaos technique in there. And on the other hand, Eric Yu proposes agent-oriented requirements engineering and describes the I-STAR modeling technique in first this paper from 1997, and then a lot of follow-up papers and more detailed research later on. Thank you so much. I will see you next time. Go model some goals. Hi, welcome back everyone. Requirements engineering. Today we talk about system visions. So what's a system vision? A system vision is essentially a big picture of the system under development and its environment. Under development and environment. So you have talked to 25 different stakeholders and stakeholder groups. You've talked to a couple of your future user groups, you've talked to your clients several times, you've talked to the people who will maintain that system over time. You have talked to your coders about what is feasible and what is technically possible. So you have a pretty good understanding of what that system could look like. There's only one problem. That picture is in your head. Now, how are you going to get that on paper and communicate it to those 25 different stakeholder groups? And that's where Monk and Howard published a paper on developing system visions that are easy enough to understand for non-technical stakeholders and at the same time transport all the important information. So the system vision, you can think about it in terms of you take some cute little icons off the internet to make visual representations for all parts of your system, and then you compose that into a picture that includes the structure of your system, the process, and the concerns. So the structure means the structure of your system under development and the systems in the domain. So system under development and in business environment and operational environment. Now those two things differ insofar as your business environment says, here's the billing unit that will take care of billing the customers. Here is, what's it called? Customer relationships management. And here is the hotline that you can call. And over here is the manager who oversees if we manage to get the return on investment. That is like your business context for your system. Your operational environment is the systems that interact with your system. So for the carpooling example, that can be your database server, your web server, that can be the fleet management that makes sure that cars get cleaned. You can see that in my head I jumped from one business model to the next one, so now it's not private people signing up, but it's a managed fleet that takes care of that. And so both of those contexts are going to be represented in your system vision picture. And then you will also represent the processes, what the user can do using system. So you want to depict that they are able to agree on a carpool, meet up at a certain time, go places, come back, get billed for it, sign up for a different modality, sign up for a different type of payment, whatever they want to do in there. And the third part that you want to show is the concerns of the major stakeholders. And typical concerns for that are, how do I keep the operating expenses down? Is my system gonna lead to any disruption in any other environment? I'm just stopping here because in the original article of Monk and Howard, one of the examples that they use in their article, and you're gonna read that today as an assignment, that they model a pub in a little city. And so one of their stakeholder concerns were the neighbors who said, well, is it going to be too noisy late at night? So that example also shows that it doesn't necessarily have to be your software system in the center. It can also be a bigger context picture that you're analyzing. So the scope of what your system vision is about can be adapted to what you need to analyze for a given problem statement. It may be an entire city if you want to develop a smart city system, and it may be something as tiny as a washing machine in its context, or something as local. Now, remember, those three parts all need to be present in your system vision, and the very simple guideline that you are likely to hear as feedback on your first draft is, can I understand what your system is about within the first few seconds of looking at it? So, major objective, And I see the system's purpose right away. Because what we want to do with that system vision is to communicate it to all stakeholders that are involved with that project. So the usage, communication with all involved stakeholders. And you want to use a lot of pictures in your system vision for two reasons. The first reason is you may have a bunch of non-technical stakeholders in there that should still be able to understand what this is about. And the second part is it just makes it a lot nicer to look at. If I don't have to read through all the font size 8 description of your diagram, but instead I have a few pictorial elements that make it easier for me to understand what it is about. So go ahead and try it.
Okay.
Yup. Hello everyone, welcome back to Requirements Engineering. Today we will talk about the usage model. The usage model, as you may recall, I have introduced when we talked about artifact models as the one where you describe the interaction between a user and the system. And we have two parts that belong to the usage model. The first one is the use case overview diagram. And the second one are the use case scenarios. The first one, the use case overview diagram, is a standard UML diagram. And for the use case scenarios, we can use the Coburn template. So this one is UML, and this one will do according to the Coburn template. The use case overview diagram is also known informally as the bubble diagram. And this is what it looks like. We have a user, and this user is representative for a user group. We have the system boundary, system under development. This boundary is the system scope. And then in here we have the use cases. And then we have a straight line from a user to a use case that denotes that this user can carry out that use case. There could also be a different user representing a different user group over here that may be a different user group called admin. And the admin can, for example, add user accounts. So we will add a different user if there are several user groups for our system. And each representative user will only be linked to the use cases that they can perform. Now the admin may, depending on how you design your system, also be able to perform all of the others. Or you can say, no, I don't want the admin to get chaos into everything. I'm going to require them to log in as an admin to carry out their admin activities, and I will require them to log in as a normal user when they want to do the other normal tasks that any other user can perform. So that's a choice of your system design. There are a couple of special cases. There is an includes and an extends. Oops, it shouldn't go in here. Includes other task. And if you write includes, that means this one is always carried out when this one is performed. And there is another option that is called extends. Other task 2, which means that this use case can be performed in addition, but it doesn't have to be. So extends denotes an optional to carry out. And this one with the includes will always be carried out. So that's our overview diagram. Now, if we pass that on to our system developers and say, here, start programming the thing, they would say, well, you're not giving me enough. I know the admin should be able to add user accounts, but I have no idea what the interaction with him in the system actually looks like. So therefore, we detail this with the use case scenarios. So we have one use case scenario per use case from the overview diagram. And this template is gonna specify a couple of meta information items that I'm gonna skip for now, but you will find them in the template online. But what it describes in detail is the scenario main steps, this is an S, very clearly so, just so you know. The scenario main steps, and that starts with some kind of trigger. For example, user clicks on something. Then number 2 is the system response. Number 3 is then again user performs the next step. System responds by. So I'm making this here very explicit because what is important is that for every user step, you want to write down the system response. If you note it down, well, first the user clicks on new profile, then the user clicks on add my picture, then the user selects their hobbies, then we have no idea what's actually going on because we only see one side. We only see the user input, but we don't see what's coming back from the system. So nobody would be able to implement it solely upon what the user does. So we need to specify both sides. So every single time when you describe a scenario, I want to see user does this, system responds like that. User does this, system responds like that. That way, it is very unambiguous what the interaction is supposed to look like for the future. And you'll get to try that out. Welcome back to Requirements Engineering. Today we're going to talk about how to scale requirements engineering for different types of projects. For that, we first have to look into factors that help us decide on how we need to tailor, and then we'll look into 3 different project sizes, typical project sizes that we may have to deal with, and how to do requirements engineering for those. So first, the tailoring characteristics. So for scaling requirements engineering, we have tailoring characteristics. Which are the indicators that help us decide on how we need to adapt the methods that we use and the tools that we use in a specific project. So first of all, we need to understand the project setting.
Do Jira is now for all teams, especially marketing teams waiting on final engineering updates so they can finalize.
That entails factors like, what is the time frame of the project? What is my overall budget? How many stakeholders do I have involved? How many different client parties do I have to talk to? How many different customer groups and user groups are involved? So essentially, how many information sources do I have to gather from? And then how much time is it gonna take to negotiate and come to a joint agreement on what should be the requirements? So first of all, the project setting. Then second, we need to understand what the knowledge of my team members is. So we need to understand how skilled are my individual team members in the application domain that the system resides in, as well as in the requirements engineering techniques that we will use. So from a couple of requirements engineering techniques, we know that when we look at them and read them, we think they're going to be easy. For example, the system vision. The system vision is this like big picture with a lot of icons on there, with a lot of graphical elements and just a few boxes and arrows and bubble clouds for concerns of the stakeholders. It looks like this super simple diagram, and it actually is. However, when you apply it for the first time, when you try to make one, turns out it's not all that easy. It takes a little bit of practice, and over time you get better at depicting the main message. And so therefore, the level of knowledge in terms of requirements engineering, say how comfortable you are with using certain techniques, matters a whole lot in scaling your requirements engineering approach for a specific project. Third one, what's the type of system that you are developing? So depending on whether this is an embedded system, or whether it's a business information system, or whether it's a cloud-based system, a web app, a mobile app, you may need different specification techniques. If I have a graphical user interface, I obviously need some graphical user interface design. If I have an artificial intelligence system that I just talk to, I don't need to worry about the graphical user interface design, but I do need to worry about how am I going to make good dialogues for this system. And then number 4 are business and legal concerns. So this involves certain business rules that may apply in the company that I'm developing a system for. This may involve some patent issues, some copyright issues that I still have to clarify before I can start rolling. That may entail some environmental constraints, some demands by the Environmental Protection Agency to make sure that the system that we're developing is not causing negative impact on the environment. So all of these concerns together, they are the set of tailoring characteristics we need to know so we can find the right approach to requirements engineering. And if somewhere in the back of your mind you're wondering, how on earth does the type of legal concerns influence the way how I do requirements engineering? Then we just have to look into the processes that each of those entail. So if I deal with, say, a rule from the Environmental Protection Agency, that is probably written in a language that is not really conducive for software engineers to know how to design that into a system. So I may have to involve a legal person to even be able to translate that into my technical language for me. For certain business rules, that may strongly influence how I'm allowed to approach stakeholders and seek information from them. So therefore we see there is quite an influence on how I do requirements engineering. Now, once we know those factors, we can look into how to scale the requirements engineering approach. We'll put that on here, how to scale. And I said we'll do that in 3 levels. So our first level, let's call it minimalistic requirements engineering. Minimalistic RE would be something that I do in an agile context, in a small scale project. Let's say I have 1 to 3 or 4 developers in my team. I have a customer who's readily available for feedback. I have a short time span over which I want to develop the system. I have a short time to market. Let's say it's maybe a mobile app. It's a game we're developing. We are riding the wave of the latest game technology, and we know we only have a window of a few months to really make money with this. After that, it's probably going to vanish from the market. So we know we don't want to spend a whole lot of time on requirements engineering, but we want to make sure we get things right because we only have a short time window. So what we would do is we would use something like user stories, which are your shortcut version of use cases that describe the black box behavior between the user and the system. And we would use a system vision rich picture. And this rich picture is important to get everybody on the same page about where we're heading. It's a jointly agreed vision by all stakeholders. And then the third part that we would need is some kind of denoting the quality requirements. So what are the expectations with regard to usability, with regard to reliability, with regard to performance of that system? Like, how fast does it need to respond when I get rid of one of the little enemies in the game? Or how fast do the bonus points have to show up in my account? And then we see from having to document only about 3 types of artifacts in requirements engineering, that's not going to take us a whole lot of time. Now we know that in an agile setting, I have a lot of iterations with the customer, so I'm going to make sure that they sign off on those user stories every single week and that they are on the same page with us in regard to the system vision. And that may also evolve over time. Like, this is not a static thing. If we're in a moving target project, that can always change and adapt over time. But that is independent from having an artifact-based approach to requirements engineering, because the artifacts can evolve over time. We just have to make sure that we trace the changes along with the timestamps. Now, if we size it up, go to medium-sized requirements engineering. Then we may have a handful, 2 handful developers, 5 to 20 developers, something like that. We would have a time span of 1 to 2 years. It could be any type of system. I have some more experienced people, some less experienced people on the team. And it's clear from my description that I have to pick some certain characteristics for the system to just be able to give you an example. But your occurrence may vary a bit from this. And so we would need a little more detailed documentation of the requirements because we have many more people involved that we need to keep on the same page. So we want to make sure that we have the stakeholders in there in a stakeholder model, that we have a goal model, and that we then again have a system vision and the use cases, which are a specification that has more detail than the user stories in an agile environment. So in a use case description, we have more of the background information, of the context information. And then we also need quality requirements, process requirements, and constraints. Now that, again, has more scope than the quality requirements up here. Here in the process requirements, we can also make statements about how we need the development process to be carried out. And we have the opportunity to write down a lot of system constraints. Now, from this one, if I want to scale it up further, if I have, say, a software system that will have a couple of hundred developers working on it, and it's going to run over a few years, and I am in a complex system domain. I'm either in the embedded domain or business information systems. All of them can grow more complex, or I have a hybrid system that includes several types as So the third one is large-scale requirements engineering. Large-scale requirements engineering would be a project that runs for several years, that involves maybe a couple of hundred developers even, and that is a more complex system. Maybe it's a hybrid system that includes business information parts and embedded systems parts. And we deal with probably a lot of interested groups of stakeholders. And because I only have limited space here, I'm going to add the ones that are not in the medium-sized requirements engineering approach. So for large-scale RE, what we want to document in addition is a business case. And then we definitely want a more detailed domain model so we can capture the operational context as well as the business context. And last but not least, we want a function hierarchy or a service hierarchy. And that hierarchy is going to give us an overview of the black box functionality of the system, but from the system point of view. So the use cases in comparison, they were still from the user point of view, and this part is then from the system point of view. That is our plugin into the next phase, into the design. So here we have the characteristics that I need to look at to understand how I need to tailor my requirements engineering approach to a specific project. And over here, I gave you a few examples of how that plays out on different levels of complexity of your project. Thank you.
There's no telling how good it'll be.
Welcome back to Requirements Engineering. I have a short one for you today. So this one is about refining requirements. Refining requirements means once I have defined my requirements on the system level, how do I get down to the more detailed subsystem requirements that I need on the subsystem level? Let's have a system and a subsystem on here. So my system is this one. It has an input and it has some outputs. And so what I describe at this level is the so-called black box behavior, denoted by BB. And then when I look into the system in the next step, I gotta break this down. So now we are in a white box view. And we have systems S1 and S2 communicating with each other and helping to process my input into an output. So once I've developed my requirements up here, and the architect of the system has taken the first decision of, oh, these are going to be the two subsystems, then it goes back to the requirements engineer, who then has to refine the requirements of the system into the requirements for S1 and the requirements for S2. Now, how do we do that? We need two concepts for being able to perform this. One is called decomposition, and the other one is called refinement. So the idea of decomposition is I had one system before, and now I have two subsystems. So I need to take my one requirement and understand what does that mean if I rephrase that requirement for subsystem 1 and if I rephrase it for subsystem 2. So if my requirement was when I press on the brake pedal in my car, the car shall slow down. Now I have several subsystems involved that help me make that come true. My subsystem 1 could be the pedal, and then the subsystem 2 could be the brake pad that is pressing on the tire. So the way how I decompose that is I have to ask myself what part of this requirement refers to the brake pedal and what part of this requirement refers to the brake pad that goes onto the tire. And the refinement part of this is what information do I have to add on so it makes sense on a subsystem level. Because if I only say, if I brake the car needs to slow down, then the object brake pedal doesn't even appear in the requirement. So therefore I also need to add information on to make more sense. So I'm going to refine this requirement into when I step onto the brake pedal with sufficient pressure. That would be another detail that I could add on. And then for the subsystem 2, I would refine the requirement for the brake pad, which was also not even mentioned in the higher level requirement. So I would have to say, if the brake pedal was pressed, the brake pads pressed onto the tire to slow down the car, appropriate to how strongly the brake pedal was pressured. So both of those, decomposition and refinement, usually come together. I think about them one step at a time. I first think about the decomposition because I know I need to get from here to here, and then I add the refinement that allows me to add more details on. So the decomposition is the breakdown, and the refinement is adding details relevant to the context. Sounds very simple, right? Now we need to go try that out with an example system, because like so many techniques in requirements engineering, the concept is super easy to get. And it turns out it does take a little bit of practice once we start applying it ourselves.
To Zuit's future boot campers or those na katulad ko na senior high school graduate na wanted to try the boot camp.
Welcome back to Requirements Engineering. Today we'll talk about tools and traceability. So when you look into companies and how they document requirements, we find a wide range of tools that they use. Pretty recent studies have still shown that many requirements live in PowerPoint slides. That is not the best place to keep them. Why not? Because it's pretty unorganized. It's not possible to manage the requirements there in any way. It's not possible to sort them. It's essentially a documentation of the perspective that the specific stakeholder gave who held the presentation, but it's not necessarily the best place to keep requirements and to work with them. So today we'll look at 3 options or 3 general categories of how we can store and document requirements to be able to work with them. And that to be able to work with them includes this important aspect of traceability. Because if I cannot trace the rationale from why a requirement is a certain way and how it was before and what it evolved into and where I can find it in the design, then it's going to be really hard once the first change requests come in. And we know, because the world isn't perfect, even if your software is perfect, change requests will roll in over time. So the first tool, if we level it up just a tad from presentation slides, what would be the next simple way how I can store requirements? Yeah, spreadsheets, exactly. So the simplest version are spreadsheets. That means I have a row number that can serve as the ID for my requirement, and in the columns I can assign different attributes or characteristics to my requirement. For example, I can assign it a priority, I can assign it a rationale, I can have a responsible stakeholder, I can have a due date for it, I can have a pointer towards the use case where it is further documented. So spreadsheets allow us for IDs, they allow for IDs, and for characteristics. Characteristics you will often also find named as attributes. So the requirements attributes can be provided along. On the next level, if we want to scale it up a little, and honestly, spreadsheets, they help us pretty far. So I've seen pretty serious embedded systems in the automotive industry, requirements all managed in a single Excel spreadsheet. That can involve thousands of requirements. So those are the largest that I've seen. Had about 10,000 requirements. I was pretty impressed. The next level, if I say, my 10,000 requirements, I don't want to have them in an Excel spreadsheet. I would like a more reliable database where several people can work with it concurrently and where my updates are stored in a controlled version history. Then I would move to a requirements database. So for more, we'll use a requirements database. That sounds fancy, but essentially it still has pretty much the same functionality that a simple spreadsheet provides us, but it scales better. So we do have simple filter functions in spreadsheets. In requirements databases, I can apply more complex filters. In requirements databases, I can also add on access rights and access policies. So I can have a certain set of top-level requirements, say the secret business policy behind what we're developing, that is only visible to executive management. And I can have different sets of people who have author rights only on subparts of the specification. So that can make sense in case I have a hybrid system with different components, and I don't want that person from Business Information Systems messing with my robot specifications of the embedded system over here. So requirements databases, they scale better. And they can grant access rights. And then the third level, because you may remember from some of the other videos that we often deal with requirements that we model in diagrams, that we don't store in a textual description. So what are we going to do with those? How are those going to go into the database? So there's two ways to do that. First of all, most requirements database tools allow for file attachments. Solved. Check. However, if we only add a diagram to this should also go in the list of capabilities. Add file to requirement. If that is a really well-modeled component diagram, then I would like to be able to select the elements in that diagram and trace that to somewhere else. So if I have a subsystem that a use case is talking about, and then I want to look into the component diagram for that same use case, there should be a link provided in between the two. But if I'm in a requirements database where I only have a graphic file as an attachment to the requirement, then that's not possible. And so for that, we have case-based modeling tools. So CASE is short for Computer-Aided Software Engineering. And those are modeling tools which means they have connected diagrams. So if you think back to our stakeholder model, and then in my stakeholder model, I can have a sub-hierarchy of user groups, and if I click on one of those user groups, then that can link me to the use cases that that user group shows up in. And therefore, traceability is very high in the case tools in between the connected diagrams, and traceability is also pretty good here. So what we ideally want is a combination of those two. There is currently no single makes everything perfect requirements engineering tool out there that would have both a large requirements database and a great modeling capacity with connected perspectives, but there are developments that are well on the way. I'm not going to recommend a particular tool or product here because I don't want to advertise for one over the other. But there are a couple of articles out there, for example, by IEEE Software, that do provide a tool comparison. So you can look into those and then draw your own conclusions. Welcome back to Requirements Engineering. Today we'll talk about quality requirements. Quality. Let that sink in for a moment while I write down the title. Why did I say let that sink in for a moment? People have very different understandings of what quality means for a specific software system. I used to open this talk by showing two mobile phones, an iPhone and an Android phone, and asking people which one they thought was higher quality. And of course that choice came back to personal preferences, because at this point of development, they're pretty even overall in their quality. Now, if you are a fan of how Apple products integrate all their services, then you may have a preference for the iPhone. If you are a fan of tinkering yourself with your phone and maybe developing your own apps, then maybe you prefer an Android phone. And those qualities are not absolute. So when you define the quality requirements for your system, the most important choice you have to make first is what kind of quality model are we talking about. So you have to choose your quality model. Welcome back to Requirements Engineering. Today we'll talk about quality requirements. Quality. Let that sink in for a moment while I write down the title. Why did I say let that sink in for a moment? People have very different understandings of what quality means for a specific software system. I used to open this talk by showing two mobile phones, an iPhone and an Android phone, and asking people which one they thought was higher quality. And of course that choice came back to personal preferences, because at this point of development they're pretty even overall in their quality. Now, if you are a fan of how Apple products integrate all their services, then you may have a preference for the iPhone. If you are a fan of tinkering yourself with your phone and maybe developing your own apps, then maybe you prefer an Android phone. And those qualities are not absolute. So when you define the quality requirements for your system, the most important choice you have to make first is what kind of quality model are we talking about. So you have to choose your quality model. But don't worry, you don't have to make it up from scratch. We do have a standard for it that you can seek inspiration from and that we tend to use in a lot of projects. So there's the ISO 25010, which provides you standard software quality models. So I recommend looking into that one. It essentially gives you an overview of what are the high-level quality attributes and quality characteristics. We're not going to go through that ISO standard in this lecture, because that makes more sense when we have slides where I can show the submodels of the ISO 25010. What we will look into is how do I specify individual quality requirements. So when I think about typical quality attributes like performance, usability, maintainability, reliability, accessibility, and so on and so forth, how do I note down a requirement for this? Let's start with a performance requirement. My requirement is the system should respond fast. Okay. Now imagine I'm passing this requirement on to my designers and my implementers. What are they going to come back with? A fast system? A really fast system? An incredibly fast system? Most likely they're going to come back with a question, like how fast is fast for you? What does fast mean in the context of the system that you're developing? Are we talking about this giant database algorithm in the back where it's reasonable to consider a 2-second response still as very fast? Or are we talking about a little mobile game, or even more intense, a safety critical system that needs to react in nanoseconds to provide safety for the surroundings? So depending on the type of system and the application context, the definition of what fast is can vary wildly. So we can have this as the initial description. But then we also want to have a metric that tells us how fast is fast. And that metric, in our case, we say response time should be less than half a second.
Pamamanhid at tusok-tusok? Take doctor-prescribed Neurobion. It's 4 times B12 versus a generic B vitamins brand. Helps relieve these symptoms of nerve damage. Ask your pharmacist for Neurobion.
Going shopping, so many fits to choose.
What we need to define next is how we're going to measure that. Like, response time from when? When the user clicks or when the system starts computing? Like, when exactly do we do that? And so the next part to define, oops, typo, that's getting worse. It's the measurement. And we probably have some benchmark tests that we've performed in the past with very precise instructions. So we can just reference that one here. Or it may be a textual description that says 25 test users are going to carry out the use cases 34 and 35, and if the response time is less than half a second, then this is accomplished. Now the last thing, there's one fourth thing that we want to denote in all of our quality requirements. Any guesses what that could be? We know the description, we know what precisely we want to be able to measure, and we talked about how we want to measure it. Take a step back. What was the most important question? What's the most important question in requirements engineering? Yeah, why? The most important question in requirements engineering is why. So why should the system respond fast? So number 4 is the rationale. And we could state that otherwise the user will switch to a different service. So this is a risk that we know we'd be running if we couldn't fulfill this quality requirement. So always know your whys. This is pretty much the structure how you could denote every single quality requirement. Now you may say, come on, this is an easy one. Performance, really? We can just put numbers on it and we're done. Let's try something else, something where it's harder to put numbers on. What would we do with usability? The system should be easy to use. What's going to be the number? What's going to be the metric that we measure here? For qualitative requirements of this kind, I have 2 ways to break them down and measure them. One way is to detail them into sub-requirements where I can find a precise metric. So that could be for usability that I decide easy to use for me means the font size is large enough to read. The colors have a contrast that does not cause a flimmer contrast for the person that looks at it. The system should have usage processes or use cases that I can complete in less than 7 clicks. All of those would be things I can put metrics on. So I can either use that way to break it down, or I can go a different route. I can leave it as a qualitative one, and I have to define a routine that would tell me when is it good enough, what is easy to use. So if I leave it on a qualitative level, that means I need a representative user group that rates the system after use and says, yep, this is easy enough to use. So either break it down into countable things, or say test user group, come on pen, 90% of test user group rated ease of use at a 9 out of 10. So that could be my metric, and then the measurement would be the test routine. Take 100 beta testers and have them rate the system after 15 minutes of use. Finally, the rationale. We don't want to forget our whys. And it's just user retention. To be honest, user retention, otherwise the user will switch to a different service, that's a very common rationale for a lot of our quality characteristics. If the system is not at that level of quality, then the user is probably going to walk off and use some competitor system that does the same thing. But there could be more differentiated ones, for example, for reliability and robustness, and for security and safety. So here are 2 examples, one where I have a direct metric that can respond to what I'm asking for in the description, and one where I go a different route of having a number of users rate my system to say whether it fulfills a certain quality. Now go try that out for at least 10 different quality characteristics. Welcome back to Requirements Engineering. I just want to do a quick clarification for you today about the term non-functional requirements. You will come across that everywhere in industry, and I want to debunk it a little, decompose it a little. I want to enable you to break it down so you can work with those. Because essentially the term non-functional requirements is kind of chickening out of really telling us what it is. It says, oh, I'm not that, but it doesn't tell us what it is. So it's pretty easy to take the functional requirements and separate them out, because they all talk about how a system behaves under certain circumstances. But when it comes to everything else, then we take a minute and think about it, or we just stuff them all into the non-functional requirements. Today we'll take the minute to think about it. So what really is going on are 3 subtypes here. And you may find a couple of different frameworks out there for it. Some have 3 subtypes, some have 4 subtypes. But you know, as with any framework, it is only a means to structuring information. That means you're going to use the one that you find most useful for the project context you're in. So I'm going to show you a simple framework with 3 subtypes. First subtype is quality requirements. Quality requirements refer to quality attributes or characteristics and break them down for a specific project. We talk about maintainability, availability, reliability, performance, usability, all those beautiful quality characteristics. So the detailed quality characteristic for a specific system. And if you want to know what those quality characteristics are, a full list of those is available in the ISO 25010. That's the standard for software quality models. Then we have a second subgroup. If you think about how to perform requirements engineering on a large scale, if we have a large company with many hundreds of developers involved, we probably have some processes of how we do requirements engineering. And if a client has certain demands on that, then we categorize those as process requirements. So process requirements, they give us details about how we want to proceed in a certain step in our requirements engineering. So they describe how the software development process is to be carried out. And then last but not least, when we have a context for our system, we have a business context and we have an operational context. Remember, the business context is what setting in business terms we find ourselves in with the system. So we have a mobile app, or we are developing a big embedded system, or we are developing in-house tools for another business unit, or we are developing products that we're going to ship to somewhere. Those are the different settings, and they all come with a bunch of constraints that we just know from the start. Like, which systems does our system have to talk to? What does their interface look like on that other system that we'll be talking to? And that information needs to go somewhere. And that's what's called constraints. So they come either from the business context or from the operational context. With those three subcategories, you have a surefire way to deal with everything that is not a functional requirement. So now you can give a good answer and a pretty straightforward of handling every time that term comes up in a software development setting in any future company that you may work at. Thank you. I will talk about requirements management. Requirements management is a pretty large number of tasks, but we're going to break down just the few most important ones today. The first one of that is rationale management and traceability. So we remember from writing down quality requirements that we always want to denote the rationale of why a requirement is specified in the way it is. A lot of people have requirements management in their head predominantly as change management, but it's actually more than that. Requirements management starts as soon as we start with requirements engineering. So that means we want to make sure that we have captured the rationale from our first elicitation meeting all the way through history. We'll talk about that history to come in a little bit, roughly about down here. For now, we'll just talk about the start. So our first iteration of requirements management, that's requirements engineering. That's where we want to make sure that we trace the rationale, that for every single requirement that we write down, independent of whether it's on the level of a goal, whether it's a functional requirement, whether it's a quality requirement, or a constraint. We want to know what was the source, where did it come from, and why is it in the way it is. And we want to be able to trace back to that source. So we also don't want to write down client. We want to write down their specific name and the date and time when it was communicated in whichever way. So that's the first subcategory of tasks that we need to deal with. The second one is requirements documentation. And that includes attribution. So documentation is the act of, I'm going to write them down in the form that is most conducive to me being able to work with it later on. For functional requirements, that may be use cases. For quality requirements, that may be a specification of the metrics and measures of how I'm going to follow up on that during testing. Attribution means all the other context information that I can choose to add to a requirement. The stakeholder where it came from, the priority it has, the time by which it needs to be completed, other use cases this one references, quality requirements that are a part of what I'm talking about in this specific requirement, that sort of things. That's what we call attribution. So documentation and attribution, that's the second set of subtasks. And now the third part, that is communication and evolution. So in this third part, we talk about how a requirement evolves over time. We have interdependencies with tasks like deployment management, like versioning, like archiving. We need to keep trace of which version of the requirement in this iteration relates to which version of the design of that particular system, and in which version of the code is that being realized and implemented. Why? Why? So when you think about your current phone, your mobile phone, it has a specific operating system on there. If you have a phone that's as old as mine, then you're going to be worrying when that operating system is not going to be maintained anymore. So while the operating systems on that type of phone evolve over time and are probably many numbers ahead of what I have on my phone right now, my hardware is so old that I cannot upgrade the software anymore. And therefore, I'm relying on them to maintain that version of the operating system for as long as they decide to. And that means for them, it still needs to be traceable what happened with those old requirements here, how did they change according to the current context of the system, and how does that play out in design and then in implementation. So that's why we want to keep track of that over time. And then we have a couple of legal concerns. And those are things like claim management and contracting. So as a requirements manager, I'm also responsible when I have claims coming in of, oh, but this should be in here, and for some reason it's not implemented, or for some reason it's implemented different from what the claimant thought it should be. And contracting in terms of what is our baseline for the requirements for which our client signed the contract. So we can make sure that they don't try to introduce some late scope creep where they get more for their money than we initially promised them, and so we're not going to shortchange ourselves. So those are your most important tasks in requirements management. For the evolution, we have one specific process that we use to break it down, and that's change management. So that is a term that you will often come across, and that we will detail in another video. Thank you.
It's here, the iSpring Suite 11. Your new companion to help you create amazing courses and align them with any corporate identity through innovative player design. With advanced appearance settings, training materials are even more attractive, and buttons including text can be customized. There is also open access to unique fonts and adaptive design. New tools include a comprehensive content library with...
Welcome back to Requirements Engineering. Thank you for making the time. Today we'll talk about change management. Change management is one of the most important activities in requirements management. And it means we have to deal with the fact that requirements change and evolve over time. One time a student asked me, hey, but like, what if we develop the perfect software system? Wouldn't we not ever have to update it? And I crowdsourced the answer. Crowdsourcing the answer is a fancy term for I asked the rest of the audience. And I asked them, well, what if we had a perfect software system? What do you think? Would we ever have to change anything? And I thought for a while. And finally they came up with the answer, well, probably yes, because the world around isn't perfect. So in an ideal world, with an ideal software system, we may not ever have to change the software, but in the real world we do. We're not going to get around. So even if I have a software system that does exactly what I want it to do, the application environment where it's going to be applied, where it's being operationed, I don't think that's a word, where it is being used in operation, that is going to change over time. Some of the constraints are going to change, some of the interfaces are going to change, and so we will have to evolve our system eventually. And that starts with the requirements. And so for change management, when I have a new requirement coming in, that gets assigned a status. And that status can either be proposed or it can be assumed. Now what's that? So proposed would be if our customer actually said it, and assumed would be if we think that's probably a good idea, even though the customer did not explicitly ask for it. Either way, what we're going to have to do with that new requirement is we're going to have to validate it. And then if it's not in, it gets denied. If it's technically not feasible, if we cannot afford it, if another stakeholder has a conflict with it, for all those reasons, or one of those, it may get denied. Otherwise, it will get accepted. And from accepted, there are two routes that we can go, depending on the type of requirement that we're talking about. Now, if you think back to the types of requirements that we had, we have one route that says designed, implemented, and tested. And we have another route that just says applied. So what do you think? Which types of requirements go this route and which requirements go that route? Take a moment to reflect. We had the functional requirements, quality requirements, process requirements, system constraints. For functional requirements, I'm going to go down here. Functional requirements definitely need to be implemented. What about quality requirements? The system has to be fast. The system has to be easy to use. Yeah, those also need to be designed for, they need to be implemented, and they need to be tested. And what about system constraints? If it says the system that we're talking to is using version 3.2.2 of a specific language that we talk in with that system, then we need to design for that, we need to implement according to that, and we need to test it. So that's going to be the lower route too. System constraints go down here. Last but not least, in this project, we're following the rational unified process. Can we design and implement that and test it? I'm pretty sure we cannot implement it, but we can apply it. So process requirements, they go this route, and they're the only type that goes this route. And then both end up as released at the very end. So this is the entire process, the entire pathway of stages and states that a requirement will go through in the course of its lifetime, maybe several times. So every version of a new requirement will go through this. I have a new requirement that goes down this route, and then it's released in version 1.0. If something in that requirement changes, we're going to do that whole thing again until it gets released in version 1.1, and so on and so forth, as often as it changes. Now, if we were to do this all the way from the first day, we would never get anywhere, because in the very early stage, like the first few days or first few weeks, depending on the size of your project, a lot is going to change in the requirements. So what is usually done is you're going to allow for a certain time period where this is not done to the full extent yet. Like, they still have to be validated, and then you move on. But only after a certain time period, you set what's called a baseline, and then from that baseline timestamp onwards, you go through the whole change process. That's it on change management. Thank you.
B-complex with vitamin E gives total nerve care. Neurogen E.
The Nissan competition is on. Show up your school spirit and get a chance to win. Join now.
Welcome back to Requirements Engineering. Today we're going to talk about research topics in requirements engineering. So I'm just going to briefly introduce a few of the topics that are currently being talked about and being worked on a lot, just to give you a bit of an overview of what the general range of topics is. And maybe you feel inspired to pursue your own research nugget somewhere in those topics, or maybe you come up with a completely new one. First of all, we can talk about scale. Software systems have been growing a lot over the past decades. So, do you remember the time when cars did not have a whole lot of software? When you could just take a wrench and take your car apart? Maybe several wrenches, and to be honest, I've never done it myself. But I do remember my dad talking about it. More recent cars, even the ones from by now almost 10 years ago, they have 1 million lines of code of software in them, or more. And so, talking about large-scale software systems and ultra-large-scale software systems is a big topic in requirements engineering. How do I deal with millions, literally millions of requirements? If I want to develop a smart home, I have this super system that has about 25 subsystems, and each of those subsystems is still complex enough. Say, one of it is light management, the other is energy management, third one is thermostat, fourth one is controlling access to the house from the doorbell to the garage to some other access routes. And each of those, again, has a number of subsystems. So if I take all of those requirements together, that makes me end up with a pretty large number. And honestly, a smart home is not even the most complex system yet that we can think about. If we think about an entire airplane, I already named car earlier. Airplane, way larger, way more complex, way more security and safety precautions. So we need to find methods that can handle that sheer quantity of requirements. I just said safety and security. Both of those are topics that are being researched independently of scale. So safety, we are automating more and more processes. We are relying a lot on embedded systems, on support systems, on decision-making systems to help us take decisions in daily life, to help us keep safe. And so we need those systems to be able to make decisions even with a certain amount of uncertainty. That sounds weird. With a specific amount of uncertainty in there, because real life conditions don't always fall exactly in the categories that we predefined. And so safety comes together with fault tolerance. And we need to understand how we can put that into requirements and how we can break that down and refine it and then design it into the systems. Security, now that we are more and more connected with all sorts of devices, and we are collecting more and more open and private data, we also come up with a whole range of new security issues. A lot of privacy issues, anything that's stored in the cloud. It's always a little iffy to whom belongs the data, when, at which point, by which provider, if I buy which service, if I just store it, or if I bought the storage server. So a lot of variables in here. So security is going to remain a big topic. Next, we have increased reliance on the environment. And that means I have a lot of sensors that pull information for me that I need to work with. And that includes sensors that embedded systems have, a car that's driving around, an airplane, a smart home. All those types of cyber-physical systems work with a lot of sensors. And their data may be precise or imprecise, and I need to make sense of it. The making sense of it is often done in a self-managed way. So we have a lot of systems that manage themselves, that maybe use artificial intelligence. And we know artificial intelligence, it's not like all of a sudden we grew a brain out of a computer. Artificial intelligence is essentially a neural network that we have trained using a certain amount of training data to be able to come to conclusions. So it's like we feed it a data set and we tell it for that data set what the 25 conclusions are that we should be drawing out of that. And then when new data comes in from outside that is similar enough to the data the system already knows, it can make decisions accordingly to what it learned before. And so over time, the decision-making process will improve if that neural network is able to learn further. Sorry, back from our little excursion into artificial intelligence to research topics in requirements engineering. So for a system that has an artificial intelligence embedded, we also need to think differently about how do we even write down the requirements for this, and how do we organize the information? How do we communicate with stakeholders about this? A lot of interesting subtopics in this one. Another one is globalization. So we have companies that work everywhere around the world, probably on the same product even. We have companies that strategically place their development teams in continents around the globe, so that in 8-hour work shifts, they can make use of 24 hours by having people around the globe work in 3 shifts, and there needs to be a good handover to not royally screw things up. So a lot of communication that needs to be understood in here, often cultural issues, and then simple technical synchronization. What's the best way of doing that? And then one more topic, as we've been developing requirements now over many years, And we often don't only develop one version of the software system, but many over the course of years, sometimes months, sometimes years, sometimes decades. And so another big issue is requirements reuse. How can I make sure that the work I perform in requirements engineering right now is also still going to serve for the next 10 versions of that same system? Has to do a lot with traceability and a lot with proper documentation, with digital curation, and is still a broad playground for research. What are the right tools to perfect reuse? How can we make it as easy as possible without losing any information or without having silly copy and paste mistakes somewhere in there and then having information that is out of date? So this whole range of research topics in requirements engineering hopefully gives you a good idea of, nope, we haven't fully understood everything yet. There is still a lot out there to explore. And I would be happy to dive a little deeper into that with you. Hi everyone, welcome back to Requirements Engineering. This time our topic is quality assurance, and let me quickly walk you through those slides here. So let's start with a little Dilbert. We all know it's not that funny because there is a lot of truth in the comics, I guess, but this one is particularly about quality assurance. So he's offering Ratbert to get hired for the quality assurance group. He said you'd be perfect. And Ratbert says, what would I have to do? Oh, you would find flaws in our new product, thus making yourself an object of intense hatred and ridicule. And Ratbert says, well, then you'd fix those flaws, and you'd respect me for... Your respect for me will grow into a special bond of friendship, right? Nope, then we ship. So we see in this little comic already what one of the troubles with quality assurance is. So it often happens towards the end of the development life cycle and does not get completed in its feedback loop into the product. Today, I want to briefly introduce the foundations of quality assurance to you. What are quality criteria for requirements engineering? What is constructive and what is analytical quality assurance? What is quality assurance for artifacts? And then what are techniques for quality assurance? So first, motivation terminology. Then what does quality for requirements documents mean? What are principles of quality assurance? And then a couple of example techniques for constructive and analytical quality assurance. To briefly remind us, what are the biggest problems in requirements engineering? Most of them incomplete and hidden requirements, and those can be very well detected by using quality assurance techniques. One of the many of them is in this example. So your users can only delete posts when logged in. Yep, yeah, correct. And then on the right side, you see the implementation. You cannot create a new post while logged in. You may only delete them. Well, that is obviously not what we meant. And so we see the red only on the left side having a different emphasis than how it is being implemented on the right. So what does that mean for us as requirements engineers? When we talk about quality assurance in RE, we usually talk about quality defects. And we talk about incorrect requirements. So we have invalid, incorrect requirements that do not reflect the intention of the stakeholder, or we have quality defects, requirements that are in themselves valid requirements, but they have qualitative defects. So they either miss the measurability, they are hard to understand, they contradict each other, or we may have a combination of those two. So incorrect requirements are often hidden due to quality defects, and the correctness of requirements is often viewed as a quality criterion as well. And for that reason, we perform validation and verification. So validation is where we check the requirements with regard to correctness, and verification is to check whether the system fulfills the requirements, and both are part of quality assurance. Quality assurance and requirements engineering specifically means the application of systematic measures for identifying quality defects and assuring the quality of requirement specifications. This is according to the IEEE recommended practice for software requirement specifications. They check for quality criteria, for example, correctness, completeness, consistency, and traceability. You'll see a more complete list on the following slide. And that examination can be conducted constructive or analytical. Now, for the quality of requirements documents, we know a requirement is a demanded characteristic of a system or process, and we distinguish a syntactic representation in form of a text table, diagram, or formula, and a semantic representation, content, informal or formal. And then a requirements document can have a number of requirements, and it also has a structure. Now we delimit that from a requirements repository that serves for storing large sets of requirements, as opposed to just a list. We already have an understanding that this is crucial, but why is it so important? We need to understand what those documents are further used for. So down in this comic, the boss says, after apparently hiring Ratbird, that in the short time you worked in quality assurance, you found a huge number of flaws in our prototype. That's my job. You're jeopardizing our schedule. The entire project will fail and it's your fault. Why is it my fault? If a tree falls in the forest and we've already sold the tree, does the tree have quality? How many angels can dance on your head? So, quality assurance often gets a bad rep because they slow down the process, whereas in fact the process is being slowed down by errors that were produced earlier. And luckily they were caught before the product was shipped. So, we distinguish as perspectives in quality assurance and requirements engineering the one of requirements documents versus sets of requirements inside those documents versus individual requirements versus then verifying that it's actually happening in the system. The principles of quality assurance, they are two-faced, constructive and analytical. So when project team members with domain knowledge apply that knowledge during the elaboration of the requirements, for example, when they pay attention to correctness, then that is called constructive quality assurance. Whereas when an external, neutral quality responsible who performs checks for, say, traceability and understandability, that is called analytical quality assurance. So constructive happens while we engineer the thing. Analytical happens after we're done with the full draft. And here we see a coarse-grained overview of quality assurance guidelines in constructive and analytical, or quality assurance techniques, I should say. And not all of it is necessarily for requirements engineering. A few are more specific to later implementation phases, but just to give you a general idea. So things that are constructive are process standards like quality criteria and linguistic rules. We have programming guidelines, so those programming guidelines, they are for the later phases, but we certainly have a lot of process standards in requirements engineering. And then on the analytical side, we have analysis using metrics or anomaly analysis tools or graphics. We have testing, dynamic, static, reviews, and we have verification, either formal or model checking. And I'm sure you've heard about a few of them in earlier courses. Now for constructive, what we like to use are reference models, the quality criteria according to IEEE 830, linguistic guidelines, and general guidelines. Reference models are, for example, our MDIRE artifact model, where I would check whether it follows the guidance of the reference model. Then the IEEE 830 recommendation on software requirement specifications. The Coburn template that we've seen for individual requirements, for individual use cases to be precise, and then the UML2 standard, where I can check whether diagrams conform to the standard. For the IEEE 830 standard, we have a list of quality criteria. Completeness. Systematically run through all the cases that you possibly can in your system. But careful, you cannot actually find that the system is complete. You can only find that it's incomplete. So it's like debugging. Consistency. You have to relate everything back to one system model. You may have a behavioral view and a static view and a function view, and they should all be able to be mapped onto each other. For unambiguity, we can check the phrasing. For correctness, we validate. For structuredness, we examine the structure, whether it's according to a certain either standard specification or whether it's just in general well understandable. And then traceability, are requirements sufficiently linked? Changeability, can expected changes in requirements be conducted efficiently? For understandability, we have to check the phrasing, the formulations of the requirements, and then the agreed uponness, we have to check with the stakeholder. What you now do with this checklist from the standard is you take it and you make your own questions for the type of document, of requirements document that you have to review. And you can be inspired by the questions before, but you have to come up with your own version if you use a different type of specification or according to the type of specification that you use. So I suggest to pause the video here for a moment and try do that for the work that we've been doing in this course for the set of artifacts. All right, we're back. So, as an example, you can, for a simple spreadsheet with requirements, let's take a really simple approach to requirements engineering. We just have all of them in one spreadsheet. Say for completeness, we're just going to read through and then ask, are there still open questions from the lead engineer, from the stakeholder, from the customer? We can check consistency in terms of checking for requirements conflicts. We can make a language check for unambiguity by letting someone else read it and check whether it could be misunderstood. For correctness, we can check with the stakeholder. For structuredness, we check whether it adheres to the template or outline and whether it has a breakdown that makes sense. For traceability, we check links between requirements in the spreadsheet and across versions of the spreadsheet. Changeability then checks dependencies between the requirements. So a high degree of dependencies means a rather low changeability because it just makes it tough to be consistent. And then understandability is checked by letting someone else read it, whether it's easy to understand. Agreed uponness, again, we got to check with the stakeholders. For linguistics, there are a couple of classic quality defects. There are lexical defects. Do we all agree on what green means? To some people, green means the traffic light is green, I can go. To other people, it means it's eco-friendly. So what does it mean in the specific context? Syntactic, I saw the man on the hill with a telescope, can be interpreted in at least two ways. Either I had to use a telescope to see the man on the hill, or the man on the hill had a telescope. Semantic, all persons have a unique national insurance number. Does everybody have that one unique number? Or does everybody have their own individual unique number? Pragmatic one, the trucks shall treat the roads before they freeze. Who's freezing? The road or the truck? And then there's weak phrases, as soon as possible. It's better to put a specific deadline. And there can be omissions or generalization. Those are pretty close together. The syntax patterns we have learned earlier in this series are like the one down here, the ease template, when, under what conditions, the system shall, should, will, process something to be processed with more process details. So that will help avoid a lot of these linguistic quality defects. So if we try to improve the phrasing of these three requirements, what would you think? The system shall respond as fast as possible. Yes, weak phrasing. So be more specific about it. Students take 10 courses per semester. Students take 1,000 courses per semester. So does that mean Each student takes 10, and overall they take 1,000. Shortly before the due date, the medium is extended unless somebody else reserved it. So for this one, we just have to figure out, did we have a reservation on the thing? And then when the due date comes up, can we extend it, yes or no? And by the fact of simply turning around that sentence, it will make it easier already. So to make it more specific, system shall respond as fast as possible. 90% of all cases, the system shall respond to all queries within 3 seconds. Second one, every student takes 10 courses per semester. And the third one, 3 days before the due date, the system checks whether the medium has been reserved. If not reserved, the system extends the lending period. Okay? All better understandable. For guidelines and checklists, what do you think? How would you write a guideline or a checklist for one of those artifacts? Try that. Put the video on pause. What are the criteria? Before you look back into the old assignment sheets where there is a checklist, I want you to think about what that checklist should be. And then finally, techniques for analytical quality assurance, checklists, quality gates, and Fagan inspections. One checklist by Lamsverde, you remember that gentleman from goal modeling, is it must always be clear what, who, when, and where. And then there are defect-based criteria, like contradictions, inadequacies, unmeasurability, unfeasibility, and poor structuring, and there can be quality-specific criteria. Is there any unspecified response in this operation to not receive an expected input value, or receiving it too early or too late? Does the logical OR of the input condition on this operation form a tautology? And we can come up with a lot more quality-specific criteria depending on how exactly we specify our requirements. Then there's domain issue-specific criteria, like what we typically face in a domain. Say automotive has different typical problems than, say, mobile phone engineering. Then we have content-related criteria where we can check templates, did we fill the fields, were identifiers used consistently, are statement types correct, and then graphical notations. Data flow consistent, is the R diagram declaration correct, or we could check formal specifications. Quality gates then are another method to do this. These are defined in your process model. We talked about them early during the course, where for your context specification, your requirement specification, and your system specification, you have an initial milestone where you roughly know how it's defined, and then you have the final milestone where the specification is accepted. All of those milestones usually check the content, the documentation, and the accordance. So content, usual quality criteria, completeness, consistency. Documentation will check compliance with format, understandability, and ambiguity. And accordance will check if a requirement is agreed upon and if conflicts were resolved. Last but not least, Fagan inspection. This is a structured process of trying to find defects in development documents, and it includes planning, overview, preparation, inspection meeting, adaptations, and follow-up control. Planning means a moderator plans a review process. In the overview, an author describes the background of the document under inspection. Preparation phase is that every reviewer examines the document in order to find defects. During the inspection meeting, a specific reader walks through the document chapter by chapter, and the inspectors point out found defects. For adaptations, the author of the document corrects the found defects according to the action plan agreed upon in the meeting. For follow-up control, the inspectors check whether the defects were fixed correctly. So remember the name, Fagan inspection, maybe you can impress somebody. Other than that, remember the general process, because it works pretty well. And then finally, the IEEE 730 standard for software quality assurance processes. So in this figure, we see the relationship between the organization and the project, and we see that there is a software quality assurance framework that can be established, or that should be established within an organization. And then for each individual project, there should be a negotiated contract. And then we have software project planning, software project execution, and software project closing, all accompanied by software quality assurance processes and activities at the same time. When we create the product, we define the project processes along with that, the software quality processes and software development processes, through to the product lifecycle support and the end of life. And last but not least, this is how we derive requirements and relationships between the levels of the requirements. So from a contract, from the point of acquisition and then the stakeholder requirements definitions, we derive stakeholder requirements and process requirements. During system requirements analysis, we then get to the product requirements, and during software requirements analysis, we refine those into software requirements. And in this little overview table, we have the software quality assurance techniques just all listed in a little more detail. If you want to look into that standard in more detail, you will find a lot of very helpful activity detailing. And I'm just going to go through those process assurance activities so we also reflect on whether our processes already live up to what we want them to be, or whether we need to improve the description of the actual process that we're following. So, finally, we looked at a couple of definitions for quality assurance and quality defects, for constructive quality assurance, guidelines and criteria, as well as reference models. We looked at analytical QA, quality gates, Fagan inspection checklists, and we looked at the IEEE 730 standard for software quality assurance. Thank you. Hi, welcome back. Today we're going to talk about requirements engineering for sustainability. When I speak about my research, I often get asked, well, what exactly do you want? Do you want sustainable software, or do you want software systems for sustainability? And my answer is both. So I want software systems for sustainability. I strongly believe that we as software systems developers can make a much stronger and better contribution to developing a more sustainable human lifestyle. And what that takes as well is sustainable software systems. So software systems that are going to last us a long time, that are not greedy in how many resources they consume, and that are easy to maintain. But I also want us to look into the purpose of a specific system. Is that going to contribute to our long-term sustainability? For some reason, we humans think we're the most important species on this planet. So usually when we talk about sustainability and sustainable development, that is for the humans and the environment along, and hopefully that'll go hand in hand, because without a well-sustained environment, we as humans are not going to make it either. So therefore, when we start talking about software engineering for sustainability, our natural start is in requirements engineering. And for that, we're going to base it in artifact-oriented requirements engineering. Why? Because it's easier to explain, it's easier to apply, and I will be able to give you a rough understanding of that within just a few minutes of this video. So artifact-oriented requirements engineering means we are going to agree on what are the intermediate work results that we are going to create, and you have a little more flexibility in how you get there. But we agree these are the intermediate milestones, and that's how you can then agree with your team who exactly is going to carry out which tasks to get there. And for the requirements engineering part, we usually differentiate between the context, the business context, or the environment, or the problem domain that we are talking about. And then the solution domain on the other side. So those are the requirements or the solution domain. If we're getting started with the context, with the problem domain, I first need to understand who are the stakeholders that I need to go talk to. So at the very beginning of our requirements engineering is find out who your stakeholders are, who are the people that you are going to need to talk to. And we will document that in a stakeholder model. That stakeholder model should definitely have at least one representative who is an advocate for sustainability for this specific system. So make sure you find a stakeholder who can represent that. If you cannot find one of those in the organization, then that organization has some work to do. What you will also probably have early on, or what you might have early on, is a business model. Either if the system is already in place and needs to be maintained, updated, reworked, overhauled, then that is a business model that has been in place previously. And they do their business processes in a certain way. And you want to check that one for sustainability as well, according to a couple of checklists. Once we have that stakeholder model and the general business model, we can start developing a so-called goal model. Now the goal model can look like this, like a tree. It might have one root node and then several sub-goals, and then these get decomposed into sub-goals again. We might have business goals up here. We might have usage goals on the middle layer that tell us about what capabilities this future system is going to have, and then system goals on the bottom. And each of them can be decomposed. Some of the goals that you will find in here, specifically as you go down to the lower layer, will also be constraints. If you want to know more in detail about the specific techniques that lead to these individual artifacts, then please go up, look up the videos in the requirements engineering course on the stakeholders and the goal model and on the business model. Now, we want to make sure that sustainability is somewhere represented here. So where does sustainability show up in that goal model? Is it reflected in the business goals? Is it reflected in the mission for the system somehow? And then once we have established that goal model and have double-checked with the stakeholders that these are really the goals we want to talk about, we can move on and develop a system vision. Now that system vision is pretty much at the border between the problem domain and the solution domain, because we will be talking about what that system is supposed to do, but we're not yet going to explain how exactly it's going to do that. So there might be a couple of actors in here. There might be some concerns that they have. There might be a system in the middle with a couple of interfaces that your users can interact with. There will be a couple of features that the system can carry out. There might be something like a user community that interacts with the system and that forms kind of a bond in between their individual users. There might be certain structural entities that this system communicates with, maybe some external databases. This up here is a UI, there's another UI. And then we want to understand how all of the concerns that come together from here, from the different stakeholders, can be put into one rich picture that's going to be your system vision that is agreed upon in between all stakeholders. And here, I would also like sustainability to show up, to be reflected somewhere, so I can double check for that. Now, after that one, I'm going to move on in two directions. One is I'm going to construct the use cases for the system. So there is going to be a usage model. Maybe I have several actors in here. Maybe I only have one, but I have my system boundary and my individual use cases that get refined in scenarios. So that will describe me still on a black box level, but in a little more detail, what exactly the system is going to help us carry out. And then from that system vision, with influences from the goal model, with influences from the usage model, we're going to develop our sustainability analysis. Perfectly 5-pointed star, right? Something like that. So we have our sustainability analysis diagram that has the 3 orders of effect. So we have the economic dimension, the individual dimension, the social dimension, technical dimension, and the environmental dimension. So our sustainability analysis diagram, we usually abbreviate it with SUSAT because the name is pretty long. This sustainability analysis diagram will look into the life cycle effects, the enabling effects, and the systemic effects. These 3 effects are taken from a model from Lawrence Hilty, or by Lawrence Hilty, and the life cycle effects, they describe the first order impacts, the direct effects that a system has on its environment, like the energy that it consumes, for example. The enabling effects are the effects that are made possible by the usage of the system. So what does this system enable the user to do, and what effects does that create as an impact in the environment, for the economy, in the social community, the immediate community. And then the structural effects, or third order effects, those describe the systemic changes that can happen over a longer period of time if many users start using the system, if it gets taken up really well. So for example, if I talk about a car sharing system, then a systemic effect could be if many people use that over an extended period of time, we have less trouble with parking space and the air quality gets better in our area because there's way less cars on the road. That can also lead to rebound effects, the structural effects. So for example, technology has become ever more efficient, which is great. Devices have become smaller, which is also great, but as a consequence, that has led to many of us owning several devices instead of just one as we used to, or maybe no digital device before that. So in the systemic effects, we can have both, or on any of these levels, we can have positive or negative impacts. And we want to make sure that in our sustainability analysis diagram, both of those sides show up. Now, mind you, this is just a diagram. This is just one overview diagram that can summarize the most important points of your sustainability analysis. And yes, you will need a document that details what is happening in these individual cells, like what are the positive effects and what are the negative effects and impacts in each and every one of those cells. All this taken together is a very brief explanation of requirements engineering for sustainability. Now, if we want to take the requirements engineering part and expand that to the entire software engineering process, that means that later on, during the design stage, I need to find the right patterns that help me implement these goals, and I need to put certain quality assurance measures in place that will help me track the metrics that I've identified for these goals and make sure that we're actually reaching the sustainability goals we set up here and our stakeholders said they cared about and we care about. So I would love for you to start putting this into practice and let me know how that works, whether that is in your student projects, whether that is in your industry projects, whether that is in your consulting business. I'm very curious to hear from you. Thank you. Hi, I have something exciting for you. We are going to be working with a pretty good stakeholder from Silicon Valley. They have just reached out to me. They want you to develop a requirement specification for an app they envision. So let me just switch over to them so they can tell you about it themselves. Give me a sec. Yo, what's cooking? So I wanted to have this dating app. It's nice to meet y'all. I'm really excited that you're developing this product for us, and I think you're super capable. Like, your prof, she said, you guys and gals are cool. Like, you're gonna get this job done. So let me tell you about my inspiration.
So again, despite its benefits, requirements engineering can be complex and time-consuming. No, stakeholders may have conflicting priorities, no, and requirements may change frequently. Additionally, translating abstract needs into specific measurable requirements can be challenging also. So requirement engineers must balance these factors, no, ensuring that requirements are both feasible and aligned with the project's strategic goals. Now, again, for the entire video, no, thank you so much for the videos that we could able to use, no, during the discussions. No? Requirements engineering is a foundational aspect of software development that involves eliciting, no, analyzing, and validating requirements to ensure a successful project outcome. So clear and unambiguous requirements are essential to avoid misunderstanding and scope creep. No? While techniques for managing changing requirements help maintain project stability, effective requirements engineering practices, no, increase the likelihood of delivering a product that aligns with stakeholder needs, ensuring a successful outcome in a dynamic development environment. Requirements engineering, again, is based on the videos that we've heard, no, and watched, no, is the process of identifying, no, defining, and validating the needs and expectation of our stakeholders in a software development project. So it begins with requirements elicitation, where techniques like interviews, surveys, and observations gather input users, clients, and other stakeholders. And this phase ensures that the team captures a comprehensive set of requirements reflecting the project goals and constraints. And after requirements analysis and validation are conducted to refine, clarify, and prioritize them. So requirement analysis helps resolve ambiguities, identify conflicts, and assess feasibility. Validation ensures that requirements accurately reflect stakeholder needs and align with technical capabilities, minimizing risk of misinterpretation and costly rework. So clear and ambiguous requirements are critical to ensuring all team members understand the project's direction and goals, no, supporting effective communication and reducing potential issues. So managing changing requirements is another essential aspect of requirements engineering. So as requirements may evolve due to new business needs or feedback, techniques like version control, traceability matrices, and agile practices enable teams to track and incorporate changes systematically. So maintaining project stability. Effective requirements, no? Effective requirements engineering, no, ensures a product that meets the stakeholder expectation improves development efficiency and increase overall project success. So I think that's it for this topic.